Sorry for the delay. We're just going live on YouTube as well, so we had a little bit of a problem. Perfect. Okay. Okay, now you're live. So welcome everyone. Sorry for the delay. Click this here. And welcome to this edition of the Memory-Centric computing tutorial here in Micro. I'm really glad to see that the room is quite full. Was not like that in previous editions. I guess this is the crowdest that we ever got, actually. So thanks everyone for joining in. This is going to be a quite high throughput tutorial. We are going to cover a lot related to process memory. So bear with me, please. I'm not going to be the only presenter, so you're not going to be bored of me. We are going to have 2 invited talks, and also some other people from the Safari Research Group is going to come here to talk about their own subjects related to process memory. So before we start, so who am I? So I'm Geraldo. I'm a senior PhD student at the Safari Research Group. I've been working with Professor Onur Mutlu since 2017, and I've been doing research on processing memory since 2016. So it's like almost 8 years that I've been working on the subject. So I'm close to graduation. So hopefully I'm going to graduate by the end of the year or beginning of next year. So fingers crossed. And I'm in the job market in case you have a job for me related to processing memory. It would be great. And if not, if you just want to chat, you can contact me via email and or check more information about me on my website. So I do research on computer architecture, mostly focused on processing memory. And a lot of the work that I'm going to talk here today is going to be about my PhD dissertation, but not only that, this is going to be quite a broad tutorial on the subject of processing memory. So if you are already familiar with the problems, you might be a little bit bored at some particular points in time because you might already know what I'm talking about. If not, I hope you get to learn the motivation behind processing memory, where we are leading to the challenges and the solutions that we are developing over time, both in academia and also in industry. So before we start, the material that we are going to cover here is more already online in our website. You can download the slides if you want to follow up what I'm going to talk about next. This is a QR code that was already here in the beginning. Hopefully everyone got it. You need 2 more minutes to get it. I guess we are good to go. So I'm going to just flash this one. And then I guess we are ready to start on processing memory. So the problem that we're trying to solve here in memory-centric architecture is a quite old problem, actually, of computing. So probably you already know this. Today, more than ever, computing is bottlenecked by data. And this is important because there are many applications that this is the case. So we have applications that are data intensive and depends on processing large volumes of data to make decisions. For example, neural networks is a classic example, particularly nowadays. We are going to see later on in this tutorial that we have several of the industry solutions targeting particular those type of machine learning workloads, in particular transformers. And the problem here is that over the times, this is particularly interesting for transformers, is that since its development in 2017, it creates its own scaling law for the parameter size. And nowadays, if you look here in the x-axis, we are going to see that the memory demands for high-end transformers have already increased from 2 to 3 orders of magnitude in the span of what, 5-6 years. So, and this is continuous scaling. This is another view of the same problem. This is from a paper called AI in the Memory Wall from IEEE Micro this year. And here they are again plotting the year of different transformers over here in red. And in green here is the memory capacity of different GPUs that are used to train and run inference on those machine learning workloads. And then you can see there is a huge gap on the capacities that of the size of the parameter footprint for those particular transformer models, and the memory capacity for a single GPU, for example. Here they stopped in 2022. Maybe it was the time that they were started submitting the paper. But the important thing here is that there is a quite large scaling that the application is facing these days in terms of capacity use. So 410 times per every 2 years. And we are not following up in terms of memory. So we are only scaling memory capacity 2 times every 2 years. And this is not only true for the trends machine learning workloads, transformers. This is also true for other memory-intensive applications. A classic example that we are using before that transformers were quite a hot topic was genomic analysis. And you are going to see here in this tutorial later on how this impacts the way that we design genomic accelerators, because the size of the human genome and other things that you might want to sequence and process is just increasing and increasing over time as well. So what we have right now is that these applications are pushing the systems to be high performance, energy efficient, and sustainable all of the same time, while you are struggling to provide such metrics as designers. And the main issue here is that data movement is a major performance and energy bottleneck when you are accelerating those applications in current hardware. And I'm going to highlight later on some numbers to give some range on this performance and energy gap. But the problem at a high level, and I don't know, my clicker is not working, is that the way that we design systems in a von Neumann architecture is leading to this problems related to performance and energy of moving data within a system. And the main problem here is that we are going to see later on is that we are processing really far away physically from where the data is stored. I'm going to give more weights to this statement later on, but this is the overall idea of the problem that we are trying to solve in processing memory architectures. So how we design processing memory architectures today? We design architectures in what we call a processing-centric systems, where we are going to all of the computation is going to be performed in a single element inside the system. And this is just follow up on the von Neumann architecture of the von Neumann machine, where we are going to divide the computing elements in a system, or the elements in the system, into those ones tailored for computing, those ones tailored for communication, and the ones tailored to memory and storage units. And each one of them are going to be highly optimized for what they want to do or what they need to be done. And this is all good. That's been working over the years. We got to the point that we got today because of this way of optimizing systems. But the fact is, what we have today is a system that is quite imbalanced. So this is just a CPU die, a cartoonish example from back in 2006. So you're going to see that's only share L2 and L3 here. So you don't have much of a deeper cache hierarchy, but that's not important. What is important here is that in the CPU die here, the red components of this picture are the ones that are actually doing computation, so the cores here, and the remaining components of the systems are either to store data, or the green components, or to move data around, so the interconnects that are not highlighted here. So the most of the CPU die, or the die that you are developing for CPUs or accelerators nowadays are tailored for storing or moving data around, because on this the way that we think about von Neumann architectures. And just yet the bottleneck of a system still becomes the memory itself, independently on how much we increase this hierarchy of memory and communication in the systems. So this is just an example of another CPU die. This is a proper CPU die from AMD. And what we see are trends to try to mitigate this data movement bottlenecks over the years in a processor-centric way is to increase the size of your cache hierarchy, both the individual elements in each level in the cache hierarchy, and also the depth of the number of caches that you have in the system. So in this processor for AMD, you can see again that the majority of the chip is just for storing L1, L2, and L3 data, because the size of the L3 cache is quite large. The same happens for other architectures. I'm not necessarily picking up on AMD here. It's just they have really nice pictures that are good to use for presentations. But again, this trend of scaling the cache size in processor-centric systems to try to mitigate this data movement bottlenecks is still going on in industry. So this is another example from AMD. Again, the CPU die from the Power 10 processors. And again, you can see that the green part here, visually the majority of the chip is used for storing data. And this goes further. So this is an example from Apple, the M1 chip. And here, what you can see is when they show the CPU die is a lot of SRAM, again, for capacity for the caches, some DRAM, in this case, embedded to the chip, and a lot of storage chips that you even don't see around in this SoC design over here. And when you try to find for the compute resources, you don't even get to see them in scale, because in comparison, the amount of silicon that you're putting to store data across this memory hierarchy is too large. So what we have today as a summary is that we have a push from the application domain. We have these applications that are more and more data intensive and depends on the data to make accurate predictions on the particular task that they want to solve, and machines that are divided in storage, communication, and computation resources, but all of the resources impact system design, but now they are impacting them negatively because there is no harmony on how they are operating or being designed over time. All of this is not a new problem. This memory imbalance that we would end up having today has already been foreseen in the past. This is a paper from Richard Seitz. It's called "Is the Memory Stupid?" And it is as a saying from the "Is the Economic Stupid?" I guess it's the excellent time to have that saying because we just have the US elections and it was that similar context. But anyway, in that paper from 1996, Seitz already said that, or in a quote, that I expected that over the coming decades, memory subsystem designs will be the only important design issue for microprocessors. So it's not only, we know that if you design a processor, you know that's a quite hard challenge to do itself, but I would argue that is one of the main components in the system that were overlooked in the past. And with what it caused was this performance and energy imbalance that I mentioned before. So from the performance perspective, this is from Onur's PhD thesis back in 2003. And in this thesis, he collected several applications at the time that Intel was using to design their processors. And then he did the CPAI stack, where he break down the execution cycles that was spending and for each component of the system and aggregates them. And then you can see that more than half of the execution cycles were spent on off-chip memory requests. At the time, 2003, there was no L3 cache for the young people. So L2 caches were already off-chip requests to the memory subsystem. And he tried to solve this problem in his PhD thesis with using smarter prefetchers. But this thread continues. This is a really nice paper from Google from 2015, where they profile their key servers applications. And this is just what is called top-down plot, where you break down the execution into 4 components. Retiring is if something is good, the application is running without a bottleneck, and then you have other sources of bottleneck in the system. The memory bottleneck being tied to the back-end bound part of the system. And then what you can see here is that most of the pipeline slots for several of those applications are spent on treating back-end bound stalls from the system. So those are further divided into core or memory, but it's easy to say that in the paper they also make that conclusion that this is actually because of the memory components of the system, of how the applications are running. So we have those problems, the strengths in the current systems. Data access is a major bottleneck in many applications, and applications are become more and more data hungry. Energy is a key metric that we need to design around. So we had a workshop in this same room here right before, and there was some people were discussing that for NVIDIA, for example, the main metric right now is energy. So energy is a key metric because we cannot continue scaling compute at the rates that you are scaling without taking into account the footprint, the carbon footprint that particular computation is going to take on the environment. So basically, now you need to have power and plants to actually power your data centers. That is not a sustainable approach anymore. And overall, data movement created by energy created by data movement dominates the currently execution of many applications. And the reason when you bring it back to current systems is that doing computation is much cheaper than moving data, or putting the other way around. Moving data is extremely more costly in terms of energy, also in terms of performance, but particularly in terms of energy than doing computation. So this is just an example from a presentation from Delhi from HiPeak 2015, where he shows here in this this particular organization that 64 bits double precision addition takes significantly more energy than accessing less energy than accessing DRAM, for example. This is just another view of the same data. Of course, those numbers are going to vary depend on the particular system that you are analyzing, but the ballpark number here is that a memory access takes 2 to 3 orders of magnitude more than doing on-chip execution of arithmetic operation, for example, or a raster file access. And this directly translates to the overall execution or system consumption for your systems. And it's not only for large data centers that this problem is a current problem today. So we went to Google back to 2018, and we were analyzing their consumer workloads that were running inside their Chromebook laptops at the time, and also in some phones. And we saw that 62.7% of this total system energy for those consumer workloads were spent on data movement. And if you look at accelerators, depending on how you design the accelerator, in this case, again, we went to Google and we are looking at the edge CPU accelerator. We saw that depending on the model that you run, the majority of the system energy for that particular accelerator, which is tailored for that particular application, is also spent on moving data around in the system, which means that your processing elements are mostly idle for some of those models, even though they should be highly utilized because you tailor that accelerator for that particular application. So basically, the takeaway from here is that we don't want to move data. If you move data, we are already consuming energy that is much, which is in the order of magnitude more of doing computation. But for us to avoid moving data, we need to design better systems. So we need to design more intelligent architectures, and that involves several aspects of the system that we are going to touch here in this tutorial that can handle data very well. So what does it mean to handle data very well, right? So first, we don't want to overwhelm the components of the system. So we don't want to overwhelm communication. We don't want to overwhelm the storage itself or the computation itself with data movement operations. So we also want to take advantage of the amount of data that we have and the metadata that the data produces to better design systems. So how can I look at the data and understand whether I should move something around or not. So take a more educated guess on what should happen in the system. Also, you want to understand the different properties of the data to know where I should place what. So if my data is hot, maybe I need to place that particular hot data nearby some processing elements. But if it's cold, maybe I need to place the data far away. So all of that would allow us to move data with fewer amount of instructions in the system. However, the way that your design systems is in this processor-centric way instead of this data-centric way. So we think first about computation and later about data. We also make design decisions that are quite specific for a particular problem, rather than look at the data that particular accelerator that I'm designing is going to process later on, right? And those decisions are also quite often myopic, meaning that I only look at that particular point on the design space and try to optimize for that instead of looking around and be more data aware on how the system is going to treat the data. So basically, what we need to move forward to try to break this data movement bottlenecks in current systems is to design more data-centric, data-driven, and data-aware architectures. And a lot what I'm going to talk about here is going to be in some survey papers that I'm going to mention here. Is one of those are this one over here. And now I'm going to enter into the specific aspects of data-centric architectures. So the main properties that we want for data-centric architectures is to process the data where the data resides. And where the data resides kind of depends. It might be that the data resides mostly on the caches or more on DRAM, which is the main memory, or more in storage. So we don't want to dictate where that we should process. We want to understand where the data would naturally fit and process in that particular location. So that would allow us to do computation with lower latency and more energy efficiency, because we want to move data fewer times in the system. Also with low cost for data and storage. So you want to use the storage and the data in a hybrid fashion so that we can amortize that cost for storage as well. You also want to intelligently manage the data, again, looking at the data and try to understand what are the properties of the data that would allow me to decide whether or not I should move it around. So going back to the first property here, process data where it makes sense. If again, I show you this picture from the AM1 chip here, and I ask you where does it make sense to place computation, you might, different people here might say different things, right? So you might say that, oh, the majority of my silicon is these black boxes, these red boxes around, so maybe I should place the computation over there. Or you might say that usually we don't access storage that frequency, maybe the best place is the DRAM or the cache itself. So the answer is that there is no correct answer for where to process the data. Is a semantic information that you need to decide based on what you're going to run. But to do that, we need to think differently from classic processor-centric architectures. So we need a paradigm shift which allow us to enable computation where the data resides and hence do computation with minimum data movement and make those architectures more data-centric. And basically, we are going to start quite simple with a slight mindset shift where we want to use the main memory as an accelerator in the system. So basically, we are going to see here several designs for this particular case where we want to add either simple or complex logic nearby my memory elements. And I basically want to offload some particular task or computation to this specialized communication or the specialized engine nearby the memory itself. So this allows us to look at memory not only as a storage, but also as an accelerator. So this idea, which is called processing memory or process near memory, I'm going to treat the nomenclature soon. But this idea of computing or using memory as accelerator is not new at all. So there have been waves on where this idea came in the computer architecture community. The one that we trace back the earlier was from 1969 with the cellular logic memory array paper, and 1970 from the logic memory compute paper as well, where the authors were proposing to add some computing elements around the peripherals or of a memory chip itself. So that trend didn't continue much further, but then in the late 90s, in the beginning of the 2000s, it came back again, this idea of processing near memory devices with one key example here was the IRAM, Intelligent RAM project from Berkeley. And it was not only this paper, there was several other architectures for that both industry and academia were looking at the time, but unfortunately that trend also is slowed down until quite recently, and we are going to see why later on. So the reason basically is that there is now a huge push from the application domain for us to design those more energy efficiency and more performance efficiency data-centric architectures. As I mentioned before, not only because the applications are becoming more data intensive, but also because the memory systems, the way that you're designing memory systems are not scaling much further in terms of latency, performance, and throughput. And this comes to the memory scaling problem that memory is facing today. Memory is quite optimized for density. So we squeeze the number of bits per millimeter square as much as we could in currently, for example, DRAM chips. This is also similar for SRAM. And this is generating some unforeseen issues that can impact the reliability of applications other than just performance and energy efficiency as well. And do you have a question?
Just curious about
the
original work going back to 1960. What were they looking at or at the time? Like we have problems that sort of reached solve problems. What were they looking at?
Yeah, those papers were not designed. They are more circuit papers. They were not. We have this application.
So they were doing it just to do it.
Exactly. Yeah, they didn't have a key application in mind to fix, but they just did it because I don't know what was the key motivation, but that was the case. So going back to the design, basically, you as a designer is squeezed in the middle right now, right? We have the application layer telling you, I want more, and I want more data. I want this data to be cheap. I want this data to be fast, and I want this data to be low cost, while the memory technology is telling you, calm down, slow down, I cannot give you what you want at the rates that you want. So we already saw a bunch of examples for the first aspect. For the second aspect, I'm going to derail a little bit. I'm an Onur Mutlu student, so if I'm not here, if I'm not talking about RowHammer, I guess I cannot leave my group. So there is this curious fact that happens that is caused by memory scaling issues, and this which is called a redisturber phenomenon. So basically, you can induce predictable amount of errors in memory DRAM chips nowadays by following some particular access pattern in your application, and we call this RowHammer. So basically, maybe you already saw this animation if you saw one of Onur's lectures. If this is just a depiction of a DRAM array, and the way that you access a row of data in the DRAM array is by including incurring some high voltage in one of those DRAM rows, which we call opening a row. And then you close that row by applying a low voltage. The fact is, if you keep doing this, if you keep opening and closing a row at the same time, you are going to induce bit flips in nearby rows in the DRAM chip itself. And then we call the row that you keep accessing the hammer row, and the nearby rows the victim rows. So basically, this is what we call the RowHammer phenomena. And back then in 2014, when you published the original RowHammer paper, we test some DDR3 chips from 3 main memory manufacturers. At the time, we were nice and we didn't write their names. Nowadays, we say which one they are. Actually, we call like manufacturer S, and then you can think about which one is manufacturer S. But anyway, basically, what was important from this test is that we could consistently induce those bit flips independently on the vendor or the memory chip that you're getting at the time. And we are not the only one that were looking at that. Google also saw something similar with the in the Project Zero that they were running at the time. And if you are interested in RowHammer, we have some retrospective papers related to that. But the important thing is that these trends didn't finish. So I have some slides later on to show that this is actually just getting worse. Now we can induce even in modern DRAM chips, you can still predictably induce redistributed bit flips in the chip. And now it's not only RowHammer, there are also other phenomena that I'm going to mention later on that can also induce similar problems. And the way to solve that is actually tying back to processing memory, is to include some way of tracking or computing inside the memory device itself. This is one of the ways of solving that problem. So I have some RowHammer experts here. They might kill me if I just say that this is the solution, is one solution. One of those are from memory manufacturers themselves. This is a paper from SK Hynix, where basically they include inside the DRAM chip itself some RowHammer counting cells, so that you can count the number of activation for a particular DRAM row, and then avoid that reaching to a RowHammer threshold. So this is a quite simple way of looking at scaling leading into processing memory designs, because we are modifying the DRAM chip itself not only to now to store data in your DRAM chip, but also to do some really primitive form of computation. And this is not the only one. There are other solutions that look into how we can design better controllers to avoid these scaling issues for memory chips. And I would argue from a processing memory point of view that is, even though people probably not would argue back with me, but that is processing memory at its finest. So what I mentioned before is that this issue with scalability is not being solved yet. So this is just some numbers that we collected in other follow-up papers, and where we saw that due to more aggressive technology node scaling, the number of hammers, the number of access that you need to do to induce a bit flip in modern DDR4 chips, I guess that was the latest result, significantly reduced over the time. So in the original 2014 paper, this number was around 140,000 activations or reads, and this number now reduced it to around less than 20K. And in a more aggressive way, we show in this ISCA paper called row press that if you just keep the DRAM row open for long enough, this would also induce redistributed bit flips, which you call row press. So this would be the extreme point where only one activation would lead to redistributed bit flips. So basically, the key takeaway here is that as DRAM cell scales down, those DRAM modules becomes more and more vulnerable to disturbance. So one way of solving this problem is that forget about DRAM. Let's look at other emerging memory technologies that maybe are not prone to those redistributed issues. And there are several proposals over there from both academia and from industry that look into alternative technologies that can be used for main memory. You're going to talk about some of them here, like phase-change memory in this tutorial. But the problem is that we don't have a winning technology yet. So basically, the takeaway here is that for us to not only solve those performance and energy problems that currently memory are facing, we also need to look now at this extra access, which is scaling reliability caused by scaling, so that we can design better and scalable systems. And again, we as a designer are just sitting in the middle, trying to avoid and design for all of those design points at the same time. So going back to process memory, that was going to be we as a designer our approach to try to mitigate those issues. And over here, we are going to take application that might be memory intensive, like database graph or media processing, and we are going to offload portions of the computation of that particular application, hopefully portions that are indeed memory intensive and are causing those data movement bottlenecks. And I just want to tell my memory device, query this table in this database, for example, or traverse this graph for me and just give me the final leaf node. And then the memory device will just return the result, hopefully reducing the amount of data that is move around when you're doing this computation. So all of this seems quite nice, and at the high level, it might work. But for this to actually work, we need to answer many challenging questions as designers. So for example, where should we put this computation, and not where? What type of computation unit should we include to the memory device itself, so that we can enable the most of the memory chip? Another issue is that once this computation is there, how it communicates to the software stack, to the system stack, that computation is available, and how can you run this computation in an efficient way. So if that's the case, how you design system compilers and language that can take the most of this now heterogeneous architecture, where we have this division of portions of computation happening on processor, portions of the computation happening on memory. We can go one level deep, and then we can think about now, how can I look at my application in a more data-centric way now, and redesign this application so that it can make use of this newly added processing component in the system itself. So all of this seems a lot, and it is, because it involves going through the computer architecture stack, most of the computer architecture stack, but we can do that one step at a time. And then in this tutorial, we are going to see how some of our solutions for those system integration challenges as well. So this brings me to the end of this first talk. We have a question on YouTube.
There's a question.
What's the question?
Do the data movement issues apply equally to CPUs, GPUs, and NPUs?
It highly depends on the breakdown, basically. So GPUs, for example, are throughput-oriented processors, where it might be easier to hide the performance drawbacks that data movement bottlenecks might cause into the system, while CPUs might use aggressive prefetchers to do so. So depending on the system, they may suffer more or less or from this data movement bottleneck, depending on the target application that you are running, of course, as well. But the sheer fact is that at some point, if you have a data-intensive application running in those processor-centric platforms, eventually, if you stress enough the memory subsystem, they are going to become a bottleneck. The range of the bottleneck for that particular system might vary depending on, of course, what your baseline. Another question?
So basically, adding a compute element in memory would add data. How do you make it practical for the real system?
Yes, I'm going to cover that in the next presentation. So yeah, so basically you need to pay for it basically at some point. So sorry, there's a question here, and then some of them yes, some of them no. So SCC is not enough to fully correct the errors caused by reduced numbers. Exactly, yeah. So it does not actually help. It's just like I was trying to show the opposite. Actually, it becomes worse over time. So it was just a motivation to say that scaling of memory systems are also a reliability concern now as well, other than just performance and energy. Do you have a question? I guess in the very end we are going to talk about that as well. But just to give you hands on that, nowadays the landscape is increasing quite a lot because we are seeing real industrial processing memory architectures hitting the market. So compiler people now have a device to actually compile the code and run into that code, and we are seeing a lot of development on for example MLR. I always have problems saying that, where they basically create dialects in LLVM targeting specifically processing memory architectures. So still there is a lot to be done because those dialects are quite limited to a particular subset of instructions, for example, linear algebra. But we are catching up now on the compiler front. There is a lot of APIs, also software APIs, that tries to alleviate the programming burden that we are going to see later on to program those architectures, but it's not completely transparent for the programmer if you do so, right? Because then you need to introduce a new execution model to the programmers and teach them how to use them efficiently. So it's still like, yeah, there is a lot of research to be done in that area. Okay, if there is no, sorry, another question. Yes. That is one way of doing it. So we are going to see here one of our architectures that we designed for graph processing, where over there we designed the different interconnect and also a different communication way protocol, so that we can communicate across these processing engines inside and across the memory chips themselves. But you can be quite more conservative as well, and depending on what you offload or and the granularity of that offloading, it might be just a simple instruction that touches one single data word in a given row inside the DRAM chip, for example. And over there, you don't need much other than just like a read, modify, write type of circuitry. Another question. Yeah, there are some studies on that and we still don't have a conclusive answer to solve this question. And this is going to be particularly worrisome for what I'm going to cover later on, what we call this processing using memory architectures, where we are going to use multiple row openings or activations to do some analog computation in the DRAM chip itself. Over there, basically, depending on how you do it, you might lead to such of RowHammer bit flips, but we still don't know exactly by how much and how you can mitigate those as well. Okay, so if not other question, I'm going to conclude with some taxonomy, so for us to be on the same page. So what I'm going to talk next is quite available in this PIM book chapter that we wrote in 2022, and there is a new version coming on soon that is going to cover the recent literature as well. And in this book chapter, we in Safari, we break down processing memory architectures into two subgroups, what we call processing using memory and processing near memory. And the processing in memory term is a more generic term to refer to both of them. So basically, what we have in a more pictorial way is that what we are going to call processing near memory is going to be any architecture where we are going to add logic near memory arrays, near caches, near DRAM, near storage to perform some sort of computation. So this is still quite similar to the von Neumann model if you go one step deeper, because we still design logic as we design a processor or accelerator or a configurable logic, but we are going to place this logic in a different place in the system. So nearby a memory controller, or in the DIMM form factor of a DRAM device, or near the, in this example here, in the logic layer of a 3D stack memory chip itself. The other way of doing what we break down on these processing memory architectures is what we call processing using memory. And here is a completely different model from von Neumann architectures, where we are going to use the analog operating principles of the memory cells themselves to do computation. So we are not going to add logic. We are not going to design logic for compute. We might add some logic around the peripherals of the circuitry of the array itself to help doing the computation, but the computation itself is going to be performed using the memory cells themselves. And we are going to have some simple primitives based on that, and we are going to eventually compose more complex operations based on those primitives. So here I was mentioning that it's different from von Neumann because now we don't have the distinction between compute and memory anymore. Memory is both compute and memory at the same time. So another way of looking into this, when someone asks you, do you want to design a PIM accelerator? This is quite common sometimes when people are generally talk about process memory, is that they don't break down exactly what they mean about process memory. So this is not yet like GPU, for example. When you think about GPU, have some winning architectures in the market, right? AMD or NVIDIA architectures where you can point, oh, iGPU is this, iGPU is that. When you talk about process memory, with the field is still getting mature, and we have different aspects of process memory currently available in both academia and industry. So usually we need to, when you talk about process memory, you need to think first on the nature of the computation. So are you talking about processing near memory or adding logic for computation, or you're talking about processing using memory? So you're going to use those analog principles of the memory cells for compute itself. You also need to take into account the memory technology that you're going to use. So are you doing this using flash memory, using DRAM memory, using SRAM or emerging memory technologies? The location that you're going to place the computation as well. So are you placing this computation in the memory controller or inside the DIMM of a DRAM chip or inside the controller of a flash device? All of those have different trade-offs. So it's a good way of thinking about those process memory architectures is as a tuple of three things: the nature of the computation, the technology, and the location where this computation is going to be placed. And this is going to define the PIM type that you're going to have into the system. And a good thing about process memory is that you can match, mix and match. So you don't need to have one single PIM type. You can have computation spread across the entire memory hierarchy if you want, in every single level. Of course, this includes complex, like really high complexity and high cost for that particular system, but is a feasible design point if you want that complexity. So I guess this concludes the taxonomy. I don't know if there's any question on this taxonomy that you're going to use later on. We can go back to this. And finally, I guess now we are all well motivated and well oiled that data movement is a huge problem and need to fix that with process memory. And next, we are going to start talking about how we can design those process memory architectures to solve those particular data movement bottlenecks. So this is just the agenda of what we have today. We have a lot to cover. As you could see, this was already a quite high throughput presentation, and we are going to keep that pace. So feel free to stop me at any point to ask questions. At the end, I'm also going to collect questions if you want to ask for something. So we are going to have 3 more talks before the coffee break. Then we are going to have the coffee break. And then we are going to talk about some other invited talks. And finally, we are going to conclude with some research challenges and open research questions in process memory. So if there is no further question on this particular subject, I'm going to move to processing near memory architectures. Okay, great. Let's move then. Okay, over Zoom. I'm sharing the screen over there.
I see the screen.
Okay, perfect. Okay, my clicker is working. There is a range problem. I'm going to. Okay, So we are going to talk next about this processing near memory architectures from what I just break down in those two ranges. And just as a reminder of something that I just said 2 minutes ago, in this processing near memory architectures, we are going to move, we are going to design logic, and we are going to move this logic to different places inside the memory hierarchy itself. So this is the easiest way of doing processing memory, let's say. And we can do that to accelerate many different applications into the system. We are going to see examples here for graph processing, some neural networks for edge devices, but there are also architectures for mobile workloads, DNA sequence analysis and mapping, which are going to see in the end of the talk, database, time series, and if you go to the literature on process memory, and you have application that you think that is memory bound and you want to accelerate with process memory, and you type in Scholar, it's pretty likely that someone already actually thought about the process memory architecture for that. So just to say that the literature for processing near memory architecture is quite vast and rich at this point, because it has been going since at least the IRM architecture from 1997. So as I recall here, we are going to move computation to near the memory, and this can be, for example, if you have a 3D stack chip, you can place this computation in the logic layer of the memory itself, the memory of the memory chip, or if you have some memory controller, you can place some computation inside that memory controller. That's why I was mentioning that those intelligent memory controllers that are designed to mitigate redisturbance issues are fundamentally processing near memory architecture, because the mitigation mechanism usually either sits on the die or in the memory controller itself. Or for example, you can place some compute units in this is a DIMM form factor of a DRAM chip. You can place the computation inside the DIMM form factor. And all of these have different trade-offs, which I'm going to mention next. So the first trade-off that you need to consider when designing processing near memory architectures is that you have a really limited power and area budget to do that particular acceleration or that particular design. Basically, we want to add computation near the memory, but we don't want to go so aggressively where we go to the other side. We start adding computes to the memory, and out of the blue, you went back to a processor-centric design where most of your key computing elements is sitting in a single place. If you want to do some computation in the memory, your memory is designed for capacity, it's not designed for compute, and you're going to have to trade off some of that compute or some of that scaling to do some computation. So the area aspect of is quite limiting. An example here is that back in 2012, there was a consortium of several memory manufacturers, where they came up with this 3D stack chip called Hybrid Memory Cube, where they had several layers of memory device and a base die that connects those memory layers together through 3 silicon vias. That was quite hype around that time, 2012, 2015, and a lot of people were designing architectures using that logic die inside the 3D stack chip itself. But the fact is that logic die was not there for the purpose of adding whatever fancy logic that you want in the architecture itself. Was there to move some of the signal integrity circuitry from the memory controller to the 3D stack chip so that they could be more efficient. So after the memory manufacturer included logic, there was some free logic that was sitting around the logic die. And at the time, the number that people were using was this 4.4 millimeter square for what they call a volt, was a column, basically, a vertical column of that 3D stack chip itself. So this is not very large. You cannot fit much compute over there. You can fit some fewer really WIMP in other costs, for example, but it would be quite hard to fit something more costly like out of order engine, for example. Now, another problem is power delivery. The memory, again, is not designed for compute. So the memory usually has its own power delivery network. And if you want to include more power, you need if you could compute, you need more power to drive that compute, right? But if you don't want to touch that power delivery network so that you don't create other problems for the memory manufacturer, you end up with quite, again, a restrictive power budget for your compute as well. So you have to consider both aspects of that area and power, so you can do your design. Another issue is thermal. So if you start adding computes inside your memory chip itself, at some point you're going to have to dissipate the heat that compute is going to generate. And usually memory chips don't have active thermal dissipation mechanisms. They use passive thermal dissipation and cooling solutions, so that if you want to have something much powerful, would need to include more efficient 3D based, especially if it's 3D stack, 3D based heat dissipation mechanisms. And there are many developments over time from techniques that are particularly tailored thermal dissipation for 3D stack architectures using processing memory chips. The third problem is the challenging of manufacturing logic together with memory. So there are commercial and also fundamental reasons why we manufacture processors in a fab and we manufacture memory in another fab, because those processors have been heavily optimized for their own key metrics. So processors manufacturing is heavily optimized for speed at the expense of the number of metal layers that we include in that processor design, in that processor silicon itself. While memory, particularly DRAM, have been significantly optimized for density. So you have way fewer metal layers when you're designing a memory chip. This means that if you have a processor with many connections and many transistors, you have fewer space to route those connections inside the 3D stack, the memory chip itself. And adding more logic layer, more metal layers inside the memory chip would significantly increase its cost and also reduces density. So it's a trade-off over there. There are also some commercial difficulties on those, which from academia. So I only have some small ideas on how hard it might be from a memory manufacturer to actually design a high-speed processor, because I guess their teams are not tailored for that. So there are also these business aspects related to this challenging manufacturing. As an example, there is a really old paper from 1999 where they tried to manufacture logic gates using DRAM manufacturing process and the vice versa. And they saw that if you do that, if you manufacture logic gates using a DRAM manufacturing process at the time, they saw the clock frequency of that particular circuitry reduced by approximately 21%. So these are quite old numbers, but what we are going to see that this is going to translate significantly to the designs that we are going to see here from industry. You're going to see that those designs are usually either using really small logic, either in other cores or fixed function units at low clock frequencies. So I'm going to highlight some works here that we did in Safari where we try to mitigate some of those challenges over here over the span of this talk. So the type of compute then you're going to place inside the memory chip itself might vary. For example, you might use general purpose programmable cores. Usually, again, as I mentioned, those should be WIMP cores that are placed near the memory chip itself. And here I'm going to highlight one example from academia and another commercial example from industry. You also can look into application and see what is the key operation that the application does, which is also potentially memory bound. And then you can design a fixed functional unit accelerator for that particular application. So that usually involves some hardware software co-design for you to design some efficient PIM architecture for that particular application. of course, at the cost of flexibility. But if you have an application that has high demands, you can accelerate that part. You can justify the cost for the architecture. And we are going to see several examples from industry here in particular that highlights those fixed functional unit designs. And finally, you can have some configurable logic nearby the memory chip itself, or you might have some, for example, some DIMM die with some FPGA logic or CGRA logic that will allow you to do some reconfigurability on the fly or for different designs. And again, we're going to highlight some designs from both academia and also from industry. So starting with the general purpose course design. So this is a paper that we did in 2015 called Tesseract, where we took some graph processing algorithms and we saw that they were suffering from scaling those graphs when running on regular CPUs, independently on if you increase the number of cores. So we increase the number of cores and we are getting diminishing speed ups for those particular applications. And the main reason was that those applications have really low arithmetic intensity. Oops. So if you look at, for example, a PageRank, which was one of those key applications, you see that when you are actually doing PageRank computation, what you're basically doing is traversing a graph and doing some multiplication and some accumulation over the nodes of the graph. So basically what you have is frequent random access because you're traversing a graph. At the same time, limit amount of computation because basically you're just updating some value after doing some multiplication. At the same time, this was around the time that I mentioned that there was this hybrid memory cube consortium, which creates this 3D stack chip, which had this logic layer that we could place some computation over there. So the main idea here was to use this 3D stack chip to embed some in-order cores inside the logic layer so that we can accelerate graph traversing and processing inside this architecture, which we call Tesseract. So here, just to highlight some key features of this architecture, as I mentioned, we just had some simple in-order cores. Those were ARM cores at the time, connected to the DRAM controllers of each one of those vaults, those 3D partitions inside the logic die itself. But usually, when you use something similar, simple as in-order core, those architectures does not have enough memory level parallelism engines or processing capabilities to extract the high bandwidth that usually we get from these 3D stack chips itself over here. Because in order for the core, for example, you use something like aggressive prefetching or order for the execution, Tomasulu, so that we can exploit the memory level parallelism, generate many memory requests on the fly so that we can potentially consume the memory throughput available for your memory subsystem. But the cores usually don't have that capability. So to solve that, we create some communication via remote function calls that allow us to offload computation across this network of in-order cores, together with some software prefetching and hardware prefetching, which allow us to basically load the vertices before we do the traverse for some of those graph processing workloads. And again, those are we have to rewrite some of the applications because this was a combination of software and hardware prefetching. So at the interest of time, I just want to mention this architecture exists. Basically, we did some evaluation in terms of energy for this Tesseract engine. We saw a significant energy reduction because we're offloading that graph traversing to the memory chip itself, and also some performance improvement, which I'm not mentioning over here. So moving forward, going for the industry level processing near memory architectures that use in all the cores. In 2019, this French startup called UPMEM creates or make public this, which was at the time the first commercially available processing in memory architectures. So here they didn't use 3D stack chips; they use regular 2D DIMMs here, those were DDR4 teams, where they basically modifying the DRAM chip to include some simple risk like processing capabilities, which I'm going to highlight next. If don't have any luck with my mouse, my pointer. So this architecture follows accelerator model. So hey, basically they provide these UPMEM teams with these compute capabilities, but they are not a replacement for your regular DIMMs in the system. So this is following a loose cup accelerator model where we need to move the data from your main memory to the UPMEM DIMMs for you to do computation on the UPMEM PIM chips. This was one design decision. It does not need to be like that. It simplifies a lot the system integration challenge that you need to face if you go for a loosely coupled accelerator model, but it comes to its own drawback. Now you need to copy data back and forth the PIM and the main memory region, which you might say that it goes against the fundamental principles of process memory, which is at some extent true. But the idea here is that hopefully the temporary data that is generated when you are processing something is going to be larger than the amount of data that you are going to have to copy in and out of those UPMEM PIM chips. So this quite resembles GPU programming. Also, the programming model is a multi-threaded execution model, which I'm going to highlight next. So this is excerpt from their original patent that they originally published. So basically here we have the main CPU, the master SoC, connected via regular DIMMs with some DDR4 chips, and these DDR4 chips have some DRAM banks and some processing cores embedded into them. So this is just the organization of those UPMEM chips. Again, you have the whole CPU, that master in that particular picture, connected with main memory and the PIM-enabled memory. And those architecture of the UPMEM PIM chip is basically of a single DIMM has either 8 or 16 DPU chips, which is the data processing engine, and depending on how many ranks you have in the chip. And inside each one of those chips, you have 864 megabytes DRAM, which is called main memory or MRAM in their terminology, and 8 of those DPU processing engines in each chip, totalizing 64 DPUs per rank. I'm going to give a little bit more details on the microarchitecture of this next. So this is just a picture. If you go, you can buy their chip, and this is what you use basically. You have the main memory CPU, your regular DRAM, and those PIM-enabled DPUs in the same memory slot as the DRAM chip for the host CPU itself. So the first question that you might ask is how you move data from the main memory to the PIM-enabled chip. And this data movement needs to be explicit. And basically, they create this SDK with some software API, which allow you basically to either serially move data from the CPU to the DPU chips, or in parallel move a large amount of data from the main memory to the DPU chips, or you can broadcast a given buffer from a main memory to the DPU chips as well. So in this current organization of the UPMEM PIM chip, there is no direct communication between the PIM chips here in the DPU DIMM. So whatever communication that needs to happen across different PIM chips needs to go through the host CPU. For example, of those communications might be for merging partial results in a reduction, for example. So this is just, again, from their patent that they file. And here you can see, again, their that PIM-enabled chip. And here we have the memory bank and place over there with some instruction cache, local cache, and also the CPU pipeline. So the CPU pipeline that they have here is quite simple. Is a 14-stage, as I mentioned, RISC like in order core per GPU, and together they also have some working RAM. So there are just some SRAM buffers for hot data or data that's being processed at the time. Instruction RAM for the binary of the application, and the 64 megabytes DRAM to store the data for that needs to be moved through the MA engines to the working RAM prior to computation. So as I mentioned, the pipeline is a 14-stage pipeline. The frequency of this processor here is quite low. It's 425 megahertz, even though it's a quite simple core. Again, this is because of manufacturing limitations. But this processor can do some fine-grained multi-threading of up to 24 hardware threads, and hopefully you can use this multi-threaded again in a throughput-oriented way, so that you can overlap the latencies and pay off for this small clock frequency. So they also specify their own instruction sets, which is quite similar to RISC, and they have their own compiler, which you can use to compile code and deploy code into that particular architecture. So if you are interested in this UPMEM architecture, I invite you to check our longer lectures or benchmark suites that we did for this particular architecture, where we took the real system and then we are stressing it to understand its limitations. And for doing that, we create a set of workloads which have different properties, and we use together in this PIM benchmark suite that can be used to test this UPMEM architecture. So I'm not going to get into details on those over here in the interest of time, but basically we keep using this architecture and trying to see what you can do in this architecture to accelerate other applications. For example, classic machine learning training, where here basically we use this architecture to accelerate things like decision trees, k-means, logistical regression, and linear regression. SPMV, which Christine is one of our invited speakers, are going to talk about more. Translational functions, homomorphic encryption, other machine learning workloads, and just now in PACT before micro, we show also how to do some distributed training for some machine learning workloads in this architecture. So yeah, so this is from the UPMEM architecture. I don't know if there is any question. Those are other workloads. Is there any question on the general purpose PIM architectures? So yeah, this question. Yes. So in that UPMEM architecture, you can decide what you're going to do. You can do asynchronous offloading or synchronous offloading. Like basically, you can decide if your CPU will stay idle waiting for the computation to come back, or if the CPU works together in that task together with the PIM cores, and then you do that in an asynchronous way. So it's up to the programmer to decide what is particularly beneficial for that for the application that you're trying to accelerate. So there is no right or wrong. Sure. So no, they are in different address space. So this is why actually you need to copy the data to the address space of the UPMEM DIMMs before the computation. And I need to say that actually there are works recently, in the past 2 years. I'm trying to remember the name of them from the top of my head, but from some of the major conferences as well, where people are fixing this problem from academia. They are using architecture simulators, which I'm going to show next, that are trying to solve like problems like, let's make these UPMEM DIMMs in the PIM address space of the whole CPU, and then there are problems related to address translation, to MMU, where the MMU sits, all of those things, and then they try to solve these problems. But the people still didn't release follow-up yet to solve this issue yet in their design. Another question?
So I went through very quickly, which
Yeah.
is absolutely fine. Can you say in general, was there a benefit to this particular approach?
So the trade-off here is quite complicated because like you cannot use much area, right? So you significantly get performance energy savings, as I mentioned for the Tesseract paper, and also performance benefits if you can write your application in a throughput-oriented manner. Because what you have when you have these general purpose processing memory architectures, we end up with a many core architecture with a lot of wimpy cores sitting together with some limited communication across them. But if your application is somehow embarrassing parallel, or you can write your application to avoid communication across engines, usually you can use the bandwidth of the memory chip to mitigate the data movement bottleneck and have 1 to 2 order of magnitude performance benefits compared to running the application, for example, in the CPU, for example.
Yeah, I guess I asked because it seems like why not use the GPU if you're headed in that direction?
Yes.
Is the energy savings that significant?
Yes. So there is another point as well that maybe was not clear because I didn't mention that actually as well. So as closer as you move the compute to near the memory, the more memory throughput that particular compute can leverage. So if your memory is your problem is memory bound, even if you can just throw a lot of GPU resources over there, eventually that HBM bandwidth is going to be your bottleneck in the system. And if you need more bandwidth at the same memory real estate, you need to move the computation inside so you can extract the parallelism from the memory chip itself. So this is also not a versus thing, like do the GPU or do the processing memory. Usually the way that you are seeing this being done, especially in industry, is in a more collaborative fashion. So you have, for example, I'm going to talk about the Samsung approach now. They have the transformers and they have GMV for generation stage. And then you just offload that particular GMV for that particular stage to the HBM PIM, HBM chip itself that have some multiply accumulate engines. And then because of that, you can leverage that memory throughput and mitigate that memory bottleneck. Okay. So move on for fixed functional units processing near memory architectures. So when you're designing these processing memory chips, as I mentioned, there are several drawbacks and limitations that you need to take into account, like area and power, and also manufacturing challenges. So if you just use the cores, let's say, forget about accelerators, just throw the cores near my memory chips for accelerating whatever, you're going to see that the performance that you're going to get is going to be subpar compared to designing accelerator for the same problem. And this is obvious, of course, because basically you have really limited area, and now you can just tailor that area for exactly the issue that you might want to solve. So this is just an example from a paper that we did again with Google. But basically, if you need to do that now to design some hardware for your PIM system from scratch, you need to understand better what are demands or the demand of your application for that particular hardware. So basically, we need to do the classic hardware software co-design, now having processing memory in mind. So these involve several steps, of course. You have your application. You need to do some profiling to identify what are the compute requirements, the performance and energy bottlenecks for that particular application. And at some point, hopefully, do some software and hardware co-design so you can have architecture tailored for that system that is high performance, high energy efficient, and can mitigate the original memory bottleneck that you are having in the beginning. So I'm going to highlight how this we follow those two steps with two walks here. We start with some machine learning accelerator for edge devices. So basically, the story here is that we went to Google and we are working on the Google Edge CPUs at the time, and we are also running those Google Edge inference networks that were of the interest of the company at the time. And those were 24 different edge neural network models that covers, at the time, there was no transformers, or it was just in the beginning, the hype was LSTM. So cover LSTM, CNNs, and some other networks as well. So we did some profiling of those models, and then we saw that when you're running those models in the edge TPU, which is already accelerator for those models, the edge TPU will suffer from performance and memory inefficiencies. And when you try to dig deeper to understand why, from the application point of view, we saw that there were significant variations within different layers and across different layers of those neural network models that would impact the hardware design of that particular accelerator. So basically, we saw that there are models that were more memory intensive and some more models that are more compute intensive, while the edge TPU accelerator was targeting both at the same time. And this was not just across models, but also within different layers inside the same neural network model. So basically, the problem that we had was that the edge TPU was a monolithic accelerator targeting different models which have different key demands. Our proposal basically was to design a framework where we would design smaller in terms of area versions of the same accelerator tailored for different properties of the different layers that we observe. And during the runtime, we decide basically which accelerator should execute each layer based on their families. And then the question might comes is, how many accelerators is enough? How many accelerators could we design to accelerate those 24 different neural network models? So what we saw is that when you actually look at the key metrics that are important to design the hardware accelerator for those layers, those metrics, as for example, multiply accumulate intensity or data reuse or parameter footprint, would group themselves into two main families of layers. The first families are what we call compute-centric families of layers, and those ones are layers where we have high MAC intensity and low parameter footprint, and also high data reuse, and more data-centric layers. And those layers were layers where we have high parameter footprint, low data reuse, and low MAC intensity. So basically, we decided to design 3 different accelerators. Again, the area of those 3 different accelerators was smaller than the original area of the Mensa of the edge TPU accelerator. And during the execution time, we have this software runtime scheduler, which based on the properties of the layers that were profiled beforehand and the given accelerator that we designed, we could schedule the layers to the more appropriate accelerator using basically a heuristics that we designed. So usually those characteristics were identified once during the setup. So those layers didn't change much over time. There was no this dynamism over here. And the output of this software runtime scheduler was basically the layer map, which would tell me if you have a CNN layer that has is high on MAC intensity, just use the larger accelerator for that. But if you have a LSTM layer that's more memory intensive, just use the accelerator that was placed in the 3D stack layer of memory of the HBM chip itself. Sure. So why choose runtime scheduler? So maybe the name here is a bit misleading, because this is not runtime when you run; it's just runtime when you actually compile the binary. So that's why I tried to say software runtime. I guess was not a good decision of naming at the time itself, but yeah, was what we call it. So basically, again, we compare this accelerator with the edge TPU itself, and we saw a significant reduction in energy consumption, and also improve in neural network inference for that Google Edge TPU accelerator. So then we have the genome sequence alignment step or design for process memory. But for that, we are going to have a talk in the very end of our tutorial that's going to discuss more of those. Then we have the industry-based solutions for fixed functional unit process near memory architectures. And it's quite interesting because we have a lot, most of the memory manufacturers other than Micron have their own setup for these process near memory accelerators PIM, which is quite nice. Micro, actually, I was in FMS and I was in their booth early this year, and I guess they also are looking to this area, but don't quote me on them. So we are going to start with the Samsung accelerator. At the time, it was called PIM. They keep changing their name. Sorry, Brian. I don't know what is the latest nomenclature. Yeah, so it was PIM. Now it then became HBM PIM, and the latest was Aquabolt. I don't know if you change it again. It was familiar with, right? So at the time, PIM basically was this 3D stack-based architecture where, interesting, they are not going to use the buffer die here to include computation, but they are going to trade off capacity or memory density for computation. So basically, they are going to remove some of the memory layers, or they are going to not necessarily remove them. They're not going to necessarily use them for memory, but they're also going to embed some compute nearby that particular memory layer. So now they have this heterogeneity of the core die here and the core die, which is basically just DRAM dies together with some memory dies with some multiply and accumulate engines. So this was targeting basically neural network inference at the time. So the processor engine that they designed highlights that quite well. So this is just a simple picture that they have in the original paper. And here, what you can see is that what they have as compute engines is some float point multiply and add engines here, and some register files that are used to store some of the input data that is read from the memory bank. Again, since this is designed mostly for neural network inference, the instruction set is quite limited to the operations that are important for that, and also the control is quite limited to only jump instructions. So this again a picture from the original paper for the chip design, and they basically keep, after 2021, they keep releasing new prototypes that follow up on that particular organization. So in Hot Chips last year, they released some of these architectures targeting now transformers, basically GPT. And they have basically three main solutions, and all of these solutions are trying to solve the memory bottleneck caused during the generation step for those transformers, and which basically you are performing GNV operations. So the first architecture, Samsung as HBM PIM, basically adds those PIM DRAM architectures together with some AMD GPUs. And they saw some significant performance and energy savings if you do the inference for those models collaborative with the GPUs and those processing memory engines. So they also have a solution targeting edge devices, where now they are not going to use the HBM chip itself. They are using low-power DDR chips and embedding that particular similar core engine here. Again, a float point addition and multiplication engine here to again accelerate transformers on the edge. And similarly, they see some significant performance and energy gains when accelerating some smallish models. They also have a scale-out solution which uses CXL-based processing near memory CXL interconnects or memory expanders, where they add, and for this one, there is no much, this from, I remember, much details on actually what is the hardware that they are adding to the CXL controller. But the main idea here is either to add the computation to the controller itself or add the computation to the memory die and then connect the memory die to the controller. And this allows you basically to increase the capacity of our memory at the same time that you are increasing the compute power as well. And again, they have some preliminary data where they see significant improvement in energy efficiency and throughput. So SK Hynix has a similar solution as well called AIM. And here, again, they are targeting neural network inference. And but they are not using HBM chips. They are using GDDR6 chips, where they include nearby a DRAM bank, some multiplier, some adder tree, some accumulation and activation functions, again targeting neural network inference. So finally, we have the reconfigurable logic. From academia, we have some work that we did at the time with IBM called Nero, but I'm going to highlight again the industry one from Samsung called IXDIM, where basically they have this die over here, which is a standard DIM. And in the standard DIM here, they add some reconfigurable logic and in FPGA form. So basically, they can use this FPGA to accelerate whatever application that they want inside this DIM over here. And what they target to accelerate is, in the initial paper, was recommendation and systems. So basically, the main operation that they do was adding different embeddings for the recommendation systems. And basically, they designed the accelerator, which basically has two different execution modes, depending if you're using that particular chip as memory or as an accelerator. And they keep doing some work on those, or people keep following up on them. And they accelerate some other applications as well, like Sparse length sum or some database primitives. So we have longer lectures on this XDIM architecture. But what I want to highlight next, we cover more or less the landscape of what is possible for processing near memory. But what you as a researcher in academia can you do, right? So you can either go for those companies and try to use their prototypes. UPMEM, you can buy the chip itself. But if you want to work on simulation, there is still already some simulations available out there that allows you to play around with those processing near memory architectures. One of those simulators is called the MoveSim. I'm going to mention it in more details in the end of the talk, but basically it's a simulator that merges together ZSIP, which is a CPU simulator, with RAMulator, which is a memory simulator, and allows you to evaluate general purpose or accelerator like processing near memory architectures. This is available online, and I guess as I said, we are going to talk about this move simulator in the end of this talk. So if you want to use explore the Samsung HBM PIM architecture, Samsung itself put off their simulator, which is available in this GitHub repository here. And this simulator is based on DRAM Sim, which is again a memory simulator. So you can play along with this. If you want to play along with the UPMEM PIM architecture, there was a really nice simulator that was presented in this year HPCA called UPMulator, which allows you to deploy UPMEM binary and also do modifications to the microarchitecture, the UPMEM chip, and evaluate those modifications, as for example, unifying the memory address space, as I mentioned here. So all of those are open source and good tools for you to have to play along with processing near memory architectures. So we are over time, but I don't know if there's any question related to that. Otherwise, you're going to move to the first invited talk. So the industry-based solutions, they have usually what they do is that they create a driver, and then they operate based on that driver around those operating systems support that would need to happen for those architectures. There are a lot of, you should have more, but there are some research related to operating systems integration challenge for processing near memory architectures, like how you do virtual memory, for example, for these PIM systems. How do I do page table walks, all of those things. But it's quite limited. So you still need to do a lot more on that particular subject for sure. Other question? Okay, thanks so much for listening to me for this long. Now we're going to listen to Brian, which hopefully is going to be much nicer. Great. Brian is going to use his own computer.
Do I need to connect to Zoom or something either? You know, share the
Good question.
screen. I'm not sure how you've been sharing that.
I'll be sharing over Zoom. Let me, if you can just join it. I don't know if I send you the link. Let me send you the link.
I don't think so.
Okay, just send you the
Send it
link.
back to my Gmail. I can't access my Samsung email.
Okay. I send you. Oh, yeah, Gmail. Yes. Perfect. This.
I do have USB, irregular USB.
Yes. You can just use this actually. Wait, let me think about this.
I do have HDMI. Yep.
Okay. So I'm going to do this,
There's the. Okay.
and then I connect the audio here. Unreliable pointer.
I'll just go to
Okay.
the computer. That's all right. Of course, Zoom wants to install updates now. Of course it does. Where's my-
I'm going to move.
Oh my gosh.
Just in case, like double the guys.
Actually, if I could present on yours, I would send you a different slide with my notes though. Would that be easier? If
Yeah.
I just let me know. Why don't I just do that? Then we don't need to deal with all this. Yeah, maybe that'll just. Oops. I didn't send you the one with all the notes and the backups and stuff. Yep. Oh. Interesting. Let's see. Looks like my Zoom is done. If that would be easier.
Okay. Here now is
Okay. Yeah. The
something is
presenter.
going on.
Okay. All right.
So many shares.
Yeah.
All right. Yeah. As long as I have the presenter view there, then that's all good.
Okay. I think that's that.
All right. So
Sorry
in that
for the
case,
delay.
that's all right. That's fine. Oops. Sorry. Let's see.
So, sorry for the delay. We had some movement bottleneck problem. It's my honor to have Brian, which I'm going to sorry, I butchered his last name. He is a associate architecture in Samsung. He did his PhD in electrical engineering at CMU in 2023. His research tackles the even growing data movement challenge by introducing programmable data-centric architectures. He currently develops the memory hierarchy architectures for the Samsung Exynos SoC. So, it's a pleasure to have you here.
All right, great. Great. All right. Thanks, Geraldo. Yeah. Hi, everybody. Feel free to interrupt with questions whenever you want. Is as informal as it needs to be. That being said, I'll go ahead and start. So today I'm going to talk about a lot of work that I've done on generalizing near data computing. So I don't think it needs to be said, but nevertheless, I think everyone knows data movement keeps getting worse and worse. Here's a popular chart showing the relative speed up over time for memory and processors up to, I think it was 2010 or so. And clearly, processing improves orders of magnitude faster than memory. Likewise, the same goes with energy. This is data extracted from Bill Delly's talk, which Geraldo showed the figure from the talk, but this is showing it in scale on logarithmic, and energy to access data is just many orders of magnitude worse than operating on the data itself. So as a result, cores don't directly access main memory as they once did many decades ago. Current processors now contain complex, distributed, multi-level memory hierarchies. Yet software still has the same monolithic view of memory. And since the memory interface hasn't changed, most management of data movement nowadays within the hierarchy is left to hardware itself. And since management is implemented in hardware, we're stuck with conservative optimizations which are invisible to software, such as replacement policies that decide what to evict down to main memory, and prefetchers that decide what data to fetch from main memory and insert into the caches. As a result, since these mechanisms are hidden from software, they cannot optimize data movement for any specific application or workload. So they have to resort to general heuristics, such as maximize overall system throughput or minimize latency. However, applications can have a wide variety of different goals. And the big issue is that each of these application domains desires different specialized data movement optimizations within the hierarchy, but hardware currently does not enable any way for software to customize the memory data path. Recent architecture conferences have been filled with proposals for specialized memory hierarchies, many of which involve near data computing or processing in memory. And by targeting a specific data movement optimization or application domain, these specialized hierarchies often provide huge speedups and energy savings. But there's a huge problem here too. Each of these optimizations requires adding their own custom hardware, which is disruptive across the system stack and prohibitively expensive due to hardware design and verification costs. Realistically, systems are just not going to have dozens of specialized accelerators within the memory hierarchy. That brings us to the motivating question for this talk. How can we specialize the memory hierarchy without requiring custom hardware for each new optimization? Fundamentally, we realize that the problem is the memory interface. On current systems, software can only perform loads and stores, which was fine for older systems with direct memory access, but as we already saw, systems are now much more complex, yet we still use the same memory interface. Hence, prior designs were forced to add custom hardware within the hierarchy to optimize data movement because the memory interface gave them no other choice. The idea behind our work is that the increasing importance of data movement motivates an increasing need to expose data movement to software. So optimizations that previously required specialized hardware can now run entirely in software on a single general purpose platform. That leads me to the two systems I'm going to present today, each of which provides programmers the ability to optimize data movement throughout the memory hierarchy. Now, Taco and Leviathan are two systems that generalize near data computing to enable software the ability to implement a wide variety of different data movement optimizations. We're going to take a closer look at each system, and we're going to start here with Taco. Taco's goal is providing the same benefits as prior near data accelerators without requiring new hardware for each optimization. Taco achieves this by adding programmable engines that run software within the hierarchy, eliminating the need for new hardware for each new optimization. We call this a polymorphic cache hierarchy because it lets software change the functionality of the hierarchy to match the application's needs. Taco's key mechanism is that hardware notifies software when data moves and lets software intervene by observing and modifying the data. With Taco, loads and storage work normally for most data. However, Taco adds this new notion of phantom data, which is data that lives only within the cache. When a core loads phantom data, an on-missed software callback is invoked on the engine to fill in the phantom data, and subsequent accesses to the data hit in the cache like normal. And when phantom data is evicted from the cache, either an on-eviction or on write-back callback is invoked, depending on whether the data is dirty. And these callbacks let software operate on data as it moves through the hierarchy, which we found is a common pattern needed by prior specialized hierarchies that's not supported on current systems. Having introduced Taco, let's look at a simple example that shows Taco callbacks in action and introduces its main components. This example focuses on a lossy compression scheme, where an object is constructed from a shared base and a private delta. And unlike conventional base plus delta, values are approximate of the originals, lossy compression. So now let's talk about different ways one might implement this compression scheme. On current systems, if an application wants to access the decompressed data, it needs to send a request up to main memory and load the compressed data all the way back into the core and then perform the decompression there. The benefit of compression here is that we have reduced memory and cache usage, which is fantastic. But the issue is that if there's temporal reuse on the data, we have to repeatedly decompress the data every single time we want to access it because the data is stored compressed all throughout the memory hierarchy. So what about hardware compressed caches? They decompress data within the cache hierarchy so that higher levels of cache contain the decompressed data. This allows applications to benefit from temporal locality by keeping decompressed data only in the private cache. Unfortunately, not only is the compression scheme fixed in hardware, but general purpose hardware compressed caches just cannot support lossy compression because hardware doesn't know which data can tolerate approximation. Now let's look at Taco. Here, the application loads phantom data corresponding to the decompressed data it wants to access. When a load to phantom data misses in the private cache, Taco invokes an on-miss callback in software to decompress the data and store it in the private cache. Unlike hardware compressed caches, the application tells Taco exactly which data can tolerate lossy compression, and other data isn't affected. And since the callbacks are in software, any compression scheme can be implemented without requiring new hardware for each one. So let's see how Taco performs on this example. We evaluate an application that computes an average over an array of compressed data accessed using a skewed Zipfian distribution. The baseline decompresses data on the core on every single access. The first graph shows the number of decompressions performed, second graph shows relative speedup, and the last graph shows relative energy. We first evaluate a type of near data computing version, which offloads every single decompression to the L2 instead of performing it on the core. It actually performs worse than the baseline because it still performs the same number of decompressions, yet it performs it at the L2, so it even loses locality provided by the L1. In contrast, Taco achieves significant speedup and energy savings by decompressing data only once when there's a cache miss. Caches then capture reuse of the popular data to avoid decompressing it repeatedly. And finally, if we compare against Taco with an ideal engine that has infinite free compute, Taco is very close because the performance improvement here isn't due to the compute resources themselves, but it's due to the fact that we're knowing when we want to compute. It's on when data moves throughout the memory hierarchy. So if we pop back up a level, Taco provides these benefits by triggering compute in response to data movement. As we saw in the decompression example, simply offloading compute into the memory hierarchy, like many prior near data computing designs, does not provide the functionality necessary for this workload. Taco provides this missing mechanism. And by opening up the cache hierarchy to software, Taco enables a wide range of optimizations using a single general purpose architecture. Now that we've motivated the need for expanding the memory interface, let's see how Taco achieves this. Taco's two main components are the programming interface and the architecture. Taco's programming interface consists primarily of three different callbacks. On-miss fills in a phantom cache line when it's first accessed and filled in the cache, while on eviction and on writeback handle the eviction of clean and dirty data respectively. And that's basically the whole programming interface. We found that these three callbacks here cover a wide range of different optimizations. And an application uses Taco by creating what we call a morph. A morph is a data type that implements the 3 callbacks. Programmers write a morph subclass, then call a register method with the morph, the cache level to execute the callbacks, and the size of the phantom address range that the application wants. And you can register multiple instances of the same morph type, but they have to be on distinct addresses. And that covers the programming interface. Now let's switch over to looking at Taco's architecture. Taco starts with a baseline multi-core processor. On each tile, Taco adds an engine to execute these callbacks. And the engine's main components are a hardware scheduler and a data flow fabric. The scheduler spawns threads entirely in hardware without going through the operating system, and the data flow fabric runs the callbacks. To see how Taco works, let's walk through an example of how Taco executes an on-miss callback on phantom data at the L3 cache. A core loads phantom address A, which misses in the L3. The cache controller checks that the address is registered with Taco, so it spawns a thread on the data flow fabric to run the callback. On-miss then fills in the data, which is returned to the core when the callback ends. And subsequent loads to address A just hitting the L1 like normal. And when the data is evicted from the L3, Taco will similarly execute an on-write-back callback. The tags indicate that the address is registered, so after the child caches are invalidated, the controller invokes on-write-back on the data. Once the callback completes, the data is evicted from the cache. And that covers the typical life cycle of a phantom cache line. And Taco adds a small amount of state to track which lines have callbacks registered and to perform address translation. In total, which adds less than 3% state compared to the L3 cache. Now, I don't want to spend a lot of time talking about the engine's data flow fabric because Taco's design actually is agnostic to the design of the compute microarchitecture in the engines. It could work with anything else. However, I will mention that we found data flow to be a great fit. And for those unfamiliar with data flow, it's very similar to CGRA logic. Sometimes it's just a difference of terminology, but it's a type of CGRA. And we found data flow to be a great fit because it's designed for computations with small instruction footprints. It supports concurrent threads very well, and it's very energy efficient. That wraps up the design. Now we'll demonstrate the full potential of Taco's polymorphic cache hierarchy through another case study. And just to give a little bit of methodology, we evaluate Taco in cycle-accurate simulation. Here we have 16 tiles, each with an out-of-order core and an engine. Now we're going to talk about another application that shows how Taco can fundamentally change how the memory hierarchy behaves. Graph algorithms exhibit a common pattern called scatter updates, where each vertex needs to update all of its outgoing neighbors. Unfortunately, cache hierarchies are very bad at scatter updates due to the pull-based nature of caches that bring in data from lower levels when there's a miss, leading to wasted bandwidth and extra synchronization. Now, Phi is a previously proposed NDC architecture that changes the memory hierarchy from pull-based semantics to push-based. When a core updates data, instead of loading the data from memory, Phi buffers the update in the cache. And subsequent updates are then coalesced in the cache. Updates are only applied when evicted. Finally, depending on the number of buffered updates in the line, the updates are either applied directly to the data or are logged for later processing, which improves spatial locality. So Phi is pretty easy to implement with Taco's callbacks. An application starts by registering a morph at the L3 cache for vertex data. And on a cache miss, on-miss provides a zeroed out cache line. And subsequent updates are simply written to this buffered phantom line. When a line's evicted, on-write-back checks the content of the line to decide whether to apply the updates in place or to log them for later, using the exact same logic as Phi. And with that, we've implemented push semantics in software. And importantly, this isn't possible without Taco, since software cannot respond to cache insertions and evictions using only loads and stores. So the Taco version of Phi demonstrates the conclusion from the original Phi paper, as shown by these results on executing PageRank. We're showing 3 graphs here. The first graph shows normalized memory accesses, second graph shows speedup, last graph shows energy. The software baseline always applies the updates in place, regular push-based PageRank. Alternatively, we have a software implementation that always logs updates, also known as propagation blocking. And logging reduces memory accesses and does get some speedup. Then we have Taco, which decides dynamically whether to apply updates in place or log them for later, reducing memory accesses further to achieve even better speedup. And further, Taco is close to ideal because compute isn't the bottleneck. It's about deciding what to do when data moves. By now, we've seen that the current memory interface severely limits application performance and functionality as data movement becomes increasingly expensive. A wide range of specialized hierarchies try to circumvent this issue by incorporating custom hardware, but this isn't a practical solution. Taco addresses the issue head-on by letting software respond to data movement, enabling new optimizations that are impossible on current systems. Oh, before I head on to the next system, does anybody have any questions about Taco? Yes, it's done in software. They're written as regular software functions. So the structure that we use is called a morph. A morph is, you can think of it just as like a class, an object-oriented class, where you implement on miss, on write back, on eviction. And then when you want to have these callbacks execute on data itself, you call a register method and you say, here's the morph class that I want, and here's how big the address range I want it to operate on. And then that register returns an address range, a pointer to this address range. And whenever the core then accesses any data in that address range, Taco's hardware within the cache, within the engine, will implicitly trigger the callbacks on it. So the core itself is still issuing loads and stores, but software can control what happens when those loads and stores reach a specific location in the cache hierarchy that interposes on the data movement within the hierarchy. Anything else? All right, very good. So having looked at Taco, now let's look at another system, Leviathan, and see how it further generalizes near data computing. With Taco, we've seen how near data computing can tackle the data movement challenge. And although Taco does a good job at generalizing certain types of NDC, it doesn't cover all NDC designs. After reviewing the wide array of work in this field, we've identified that most NDC proposals tend to fit within 4 common design paradigms. Data-triggered NDC, such as Taco, involves computation triggered when data moves across levels of the memory hierarchy. With task offload, the core explicitly invokes or offloads a short computation to execute closer to data within the hierarchy and often returns data back to the core. Long-lived workloads involve a long-running task executing closer to main memory, often to avoid polluting the core's private cache. And streaming involves a decoupled producer running in the cache and feeding data to the core. Each of these paradigms has separately demonstrated the potential for significant data movement savings throughout the memory hierarchy across various proposed NDC systems. So what's the problem? Although there are many NDC proposals, each one targets a limited application domain while requiring its own hardware and software support. Even programmable systems such as Livia, Distia, and Taco only support the ability to implement a subset of NDC optimizations. No prior system is able to support all of these common NDC paradigms. This is a problem because different optimizations require separate hardware and programming interfaces, not to mention that some NDC designs actually want to have multiple paradigms supported on a single system to achieve their full benefits. Another drawback of prior systems is that programmers are forced to reason about microarchitectural parameters for each system they use. So what do I mean by this? As an example, imagine an array of 24-byte objects divided into 64-byte cache lines. Many objects will be split across cache lines because it will be split across distributed caches because contiguous cache lines often map to different cache banks. As a result, near data tasks can only execute near part of the object, losing locality benefits from near data execution, or requiring programmers to carefully pad and align all their data. And what about objects larger than a cache line? They will almost always span cache banks, forcing programmers to limit their objects, their data, to within a cache line size. Thus, prior near data computing architectures require programmers to reason about cache line size, which is an unnatural and limiting programming interface. To overcome these issues, we propose Leviathan, a unified system for practical near data computing. Leviathan supports all 4 NDC paradigms discussed earlier on the same system. And it does so by incorporating a near data engine, similar to Taco, on each tile of a multi-core processor. However, Leviathan's engine has microarchitectural support for all of these paradigms. And to alleviate the issue of hardware abstraction, Leviathan provides an object-oriented programming interface and then performs all data management invisibly to the programmer, ensuring that near data actions always have their data locally. So to help describe Leviathan's design, I'm first going to show a simple example application that benefits from task offload. Linked lists are a simple yet very common data structure. To find a given node's data, a thread must traverse the linked list one node at a time until the desired data is found. Let's look at the data path for a normal linked list traversal where the data is spread out across the last level cache. The thread needs to pull each node from the remote cache banks one at a time, and each node incurs a costly round-trip latency over the on-chip network. Now let's see how task offload can improve this traversal. This time, the thread offloads a lookup to the location of the first node, which itself offloads the next lookup, and so on until the data is found and returns the final result back to the thread. As we can see with task offload, each lookup only incurs a single network traversal, significantly reducing the total amount of network traffic and the lookup latency. So with the context of this example, let's now look at how Leviathan supports NDC, starting with the programming interface. We first look at the core's point of view. For NDC paradigms that return data to the core, we provide a future mechanism, which is simply a structure that provides the data to the core when it's available. Let's walk through the linked list example. When a core offloads a task using invoke, it's provided a future, and I'll explain a little more about invoke later. The core then waits on the future until the result's ready. The offloaded task can invoke more tasks, which eventually sends the result back to the future on the core, waking up the original thread and providing the result. And although this example only shows task offload, streaming interface also uses futures. Now in Leviathan, all paradigms are implemented through an actor-based interface. An actor is a type that combines data with near data actions that may operate on that data. In this example, the actor is a node in a linked list containing a key, a value, and a next node pointer. The near data action for this actor is a lookup, which checks whether the input matches the node's key. If the lookup finds the key or reaches the end of the list, it returns a value that is sent back to the invoker's future. And here we see how a core explicitly invokes the near data action using task offload with the invoke keyword. And also notice that it's possible for actions to trigger further actions, as is necessary with pointer chasing, where any given node might not have the data you're looking for yet. Another critical component of Leviathan is its memory allocator. The interface is very simple, just two malloc-like allocate and deallocate methods. The important point is that the allocator is the way in which applications inform Leviathan of its data access granularity, enabling Leviathan to perform data management behind the scenes. Earlier, I showed why it's important for objects not to split across cache lines for near data computing. One of the roles of the allocator is to automatically pad objects to avoid the splitting. Later, I'll also show how we enforce locality for objects larger than a cache line, but that requires additional hardware support. And importantly, Leviathan only pads objects within the cache, since Leviathan's hardware has further support to recompact data before it reaches DRAM. Now, I'll briefly describe how to program each of the paradigms. First, task offload and long-live are programmed similarly. There are minor differences, such as long-live being less likely to return a value, but they both involve a core or a near data action explicitly triggering another action. Beneath the example actor here, we see how an application can allocate an actor instance using Leviathan's allocator, and then invoke an action, which sends the computation out into the memory hierarchy. Next is data triggered. The underlying mechanism is essentially Taco, but since actions now execute on actors instead of cache lines, on miss becomes the actor's constructor, and on eviction and on writeback become the actor's destructor, with a dirty flag to distinguish which one. Finally, streaming involves an actor with separate producer and consumer interfaces. GenStream is the near data action, which must be implemented to populate the stream using the push method. And then the consumer, running as a regular thread on the core, uses the next function, which returns a future that contains the next value when it's available. Now let's move on to looking at Leviathan's architecture. At the system level, Leviathan's essentially the same as Taco. Leviathan augments a baseline multi-core system with an engine on each tile. The improvements are in the engine and the data management support. Leviathan's engines build upon Taco's by adding microarchitectural support for each NDC paradigm. The task offload scheduler checks whether an actor's data is cached locally, and if not, it will forward on the action to the next level of the hierarchy. The data triggered scheduler maintains a buffer of actors currently being constructed or destructed, and determines which action should be executed on cache insertions and cache evictions. And the stream scheduler maintains head and tail pointers to a per stream buffer for each stream, which is stored in shared memory. So I already showed how Leviathan's allocator pads small objects to map to a single bank, but mapping objects larger than a line requires some additional hardware support. For distributed caches, the bank which an address maps to is determined by hashing the address. So for objects that span cache lines, those lines will likely map to different LLC banks. Leviathan, to overcome this, adds the object size to the data's TLB entry, so that the least significant bits of an object's address can be zeroed out. For this example, if you have an object spanning 2 lines, we only need to zero out one of the object's address bits. And as a result, every cache line address for an object provides the same input to the hash function, ensuring that large objects all map to the same cache bank. And of course, we still pass the full address to the cache bank to do the tag lookup, but to determine which bank to map to, it's perfectly fine just using a subset of the address. Leviathan's remaining microarchitectural mechanisms include compressing padded data in main memory and additional minor per paradigm support. In total, the hardware overhead, including the engines, is a little over 6% compared to the LLC. Now, let's look at Leviathan's quantitative benefits through 2 more case studies. And the evaluation methodology, once again, similar to Taco, we evaluate a 16-core CMP, where each tile contains a core and an engine with data flow fabric. The first case study we're going to look at demonstrates the benefits of Leviathan's transparent data management. Hash tables are a popular data structure due to their theoretical O(1) lookup time. However, practical lookup time is actually determined by conflict resolution. Conflicts are commonly resolved by having a linked list per hash table bucket. And I've already showed how we can implement linked list traversal with Leviathan. Now, a major benefit of Leviathan is that the programmer does not have to worry about the size of each linked list node. So let's look at how Leviathan performs on hash table lookups across a range of different node sizes. This evaluation shows results when iterating over hash table buckets using a uniform distribution. We're first going to look at speedup. Now, compared to the baseline of performing all lookups on the core, we evaluate Leviathan with and without its padding and large object mapping, and also Leviathan with an ideal engine. The first group of bars here shows results when all the linked list nodes are equal to a cache line size, which is what's been done in prior work. We can see that Leviathan provides a substantial 2x speedup. For smaller 24-byte objects, Leviathan provides similar performance. And without Leviathan's padding, performance significantly degrades because these 24-byte objects will frequently span cache banks. So near data tasks still have to grab data from a separate bank, reducing the benefits of near data computing. And when evaluating large nodes that are equal to 2 cache lines in size, Leviathan still performs well, which is not the case without Leviathan's large object mapping. And if we look at energy, across the node sizes, Leviathan significantly reduces energy, both fewer network traversals and by executing lookups on more energy efficient engines. As we can see, Leviathan's padding and large object mapping support do indeed reduce the amount of network traffic. Now, the final case study we're going to look at demonstrates Leviathan's ability to support NDC optimizations that require multiple NDC paradigms together. So we already saw how Taco implements phi, but that actually isn't the whole story. Now, let's quickly walk again through how phi works. When a core updates data, instead of loading data from memory, phi pushes the update into the cache. And subsequent updates are coalesced in the same location. Then when the data is evicted, depending on the number of buffered updates in the line, you either apply the updates directly or you log them for later processing. Now, processing data on eviction is a type of data-triggered NDC, and that's what Taco supports. However, pushing these read, modify, write operations into the cache is actually task offload NDC as well. So phi is technically a multi-paradigm near data computing architecture. And since Taco does not support task offload, it cannot fully implement phi. Accordingly, Taco implements the updates as atomic instructions on the core, resulting in data ping-ponging between the cores. Leviathan is the only general purpose architecture that can fully implement phi due to its multi-paradigm design. Now let's see the quantitative benefits provided by Leviathan when running PageRank with phi's design. The left graph shows speedup, the right graph shows energy, both normalized to regular push-based PageRank. First, we see Taco when using normal fenced atomics on the core. Although it does support data-triggered NDC, performance barely improves because of serialization of atomic updates on its cores. Thus, Taco is actually forced to use relaxed atomics, which are not typically supported on commercial processors, but have been proposed. And that is how we evaluated Taco in the previous evaluation. And when Taco does have relaxed atomics, it is able to achieve notable speedup. However, this still is with all the atomic updates executing on the cores. Leviathan achieves additional speedup and energy savings by more accurately implementing phi using its multi-paradigm design, and without requiring additional support for relaxed atomics on the core. Finally, performance is similar to an ideal engine, since the NDC actions are relatively simple and short. Leviathan builds upon abundant prior work in near data computing to provide a unified general-purpose NDC system. By supporting multiple paradigms and providing a simple-to-use actor-based programming interface, Leviathan paves the way for practical near data computing. In summary, near data computing is a fantastic way to reduce data movement, but it isn't scalable to implement separate hardware and software interfaces for each new design. To make near data computing truly practical for general-purpose systems, architectures must enable software a way to implement a wide variety of optimizations on a single platform. And thank you. Questions?
Defer operation, how much can you defer? Is there a bunch of memory associated with how many deferrals can be held at a time?
Are you talking about with PHY when you're logging for later? So there's no limit to the limit to that is memory capacity. You're simply main memory in that case. You're writing to regular non-phantom data in that case. That design is based on the original propagation blocking paper, where it simply noted that if you have very sparse updates, it's better to batch together updates that will all update a contiguous region of memory. So you're just appending to a regular log. It's just a regular a queue of data that's stored in main memory in that case. There's nothing unique about that particular. With coherency for this case, the only thing you have to be careful about is when you're writing to the log that you don't have multiple different threads that are writing to the log at the same time. So you do have to have atomicity on appending to this log. But like if you're doing the updates in place, there's a one-to-one correlation between the phantom cache lines and the non-log data. So you're not going to have concurrent writes to that same data. So the only thing you need to worry about in terms of data correctness here is having atomicity to the log updates. But coherence works like normal with either regular data or phantom data. Any more questions? All right. Thank you. Thanks. Yeah. Oh yeah, yeah.
That is it. Yes. So let's take a 15 minutes coffee break. Hopefully, there is still coffee there, and then you come back at 3:32. Conclude the wrong. 3:32. Yeah, does not need to be that precise, but. You know. Because then talk about then I'm going to I didn't use any open source.
It's fine. Yeah, I can.
Do you want to use their computer or do you want?
Yeah, I'm gonna use mine.
Right. Okay. Well,
you're gonna continue with the processing memory stuff, right?
So I changed it just dynamically change the program.
Yeah.
Because and then I have Christina. And then I'm going to start using and then it's you. Then
So
you.
3:30 should start.
3:30 starts.
And then you end up.
I can also send you the slides if you found the setup.
Yeah, everything here. Yeah.
Okay, let me send you. Bye.
Okay, thank you.
Well, 4:30.
I think I'm going to cut the last presentation. No, I have like a concluding remark.
Just conclude. I mean, you should do.
I don't have I have
Just
slides
do
to
the last
conclude.
100 concluding remarks now. All 100 concluding remarks.
Would you like to change this? Yeah, you said when you change the line, you just.
The worse you become with IT. If it works, it
Okay.
okay.
Okay. This one.
Using if you're not moving away and you don't want
Okay.
you should pick it up.
I think I will move a little bit.
Then maybe
Yeah. I can just keep it.
It's also near.
Yes, I cannot hear you.
So, can you hear me now? If I keep it like here, like this,
So it should be close.
like this.
Yeah. So I believe that you're on the.
Okay. So very convenient. Okay. Yeah, but how it looks like? It looks like it's hanging here. Maybe I can try here. Maybe that would be very close. You can say Yanula. I mean, yeah.
Yanula.
Yeah. Now it's better. You don't need to read everything.
She's great.
Yeah. Yeah.
So now we have another invited talk. We did some reordering, some dynamic reordering based on Christina arrived a little bit earlier. So you're going to continue with processing near memory architectures. We're going to go back a little bit to DRAM again. So Christina is postdoc right now in the University of Toronto, and she worked with us in the Safari research group for some time. But finish your Christina? So 22. Yes, where she worked on processing near memory architectures. So Christina, feel free to start. Thank you so much for being here.
Yeah.
And let's go back to it.
Thank you for the introduction. Okay, so how everyone? So today I will be talking how to optimize sparse computational kernels in processing memory architectures. So nowadays we have many data that are actually quite sparse. So here I have a small road network that is like around Austin. And you can see that between those cities, some of them, they are not connected. So there are some connections that are missing. And those connections are basically represented as zeros in the data representation that we use. And this is like a very small road network, but you can imagine if we have like a very large road network with many cities, there are many zeros and many connections that are missing. And similarly, if we take a look at some sparse tables that we use in databases, you can see here like some recommendation data. And you can see that some of the users, they have not rated all the products or all the movies that I have here. So some cells are like zeros and some basically cells are missing. So they are not like, not all the users have rated all the products and all the movies here. And these sparse data are basically widely used in many applications. like for example, in graph analytics, databases, and bioinformatics, and all of them. So the key question that we are targeting to look at this project is how we can accelerate the sparse computational kernels. The sparse computational kernels are like some sparse matrix multiplications that basically do some calculations on sparse data. So if we go and look at the characteristics of the sparse computational kernels, we will see that whenever we execute a sparse matrix vector multiplication or a sparse matrix multiplication, the accesses that we get due to sparsity, the memory accesses are quite random. They are not like sequential or strided. They are basically characterized based on the input, wherever, if we have non-zero elements on the input. And this creates very irregular data accesses on the memory side. And also the second characteristic that these kernels have is that they typically have low arithmetic intensity. This means that they perform only a few computations, but they need to access a very large amount of data. So if we take a look at the roofline model, these sparse computational kernels are typically on the memory bound area, and they are typically bounded by the limited memory bandwidth that we have in our systems, in the commodity CPU and GPU systems. So at the same time, we have seen that processing memory systems are very flexible in terms of the memory bandwidth. They have a very large aggregate memory bandwidth. They have very high levels of parallelism that they can expose because we have a very large number of PIM cores very close to memory. And they also have low memory access costs. So these PIM systems, they are actually a very good fit for sparse computational kernels. They seem to be very promising. So the challenge that we have to solve is how we can effectively map these sparse computational kernels in real PIM systems. So if we take a look at the real PIM system, we will see that there are many architectures and many products from Samsung, from SK Hynix, and also from UPMEM PIM. And these are like slightly different architectures, and they have their own custom APIs and software stacks, which are very specialized APIs, and typically they are low-level programming interfaces. So the programmers need to very carefully distribute the sparse data across 2,000 memory arrays that we have in these real PIM products, and typically they need to have some expertise on the underlying PIM hardware, on the underlying PIM architecture. So overall, the programming these real PIM architectures is not an easy task. It's a very hard task actually. So our goal is basically to bridge this programming gap between developing a sparse application and running these sparse computational kernels on real PIM architectures. And we need to use a very high level and user-friendly API in order to develop the sparse applications for PIM systems. Okay, so today I will briefly go over two of our works on this direction. First, I will describe Sparse-P, which is a software library. It is written in C. And in that library, we accelerate the sparse matrix vector multiplication kernel on real PIM systems. And I will very briefly discuss PyGym, which is a graph neural network framework where we can develop graph neural networks on a real PIM device using a Python interface there. Okay, so in this library, we accelerate the sparse matrix vector multiplication kernel, which is basically widely used in graph processing, graph data analytics, and in HPC, in the HPC domain, and it is also highly bounded and limited by the memory bandwidth. And the architecture that we target to accelerate this kernel is a near-bank PIM system. So the characteristic of the near-bank PIM system is that we have one core very close, tightly integrated with a DRAM bank. So the PIM core can only access data located in the local DRAM bank, but we cannot access data allocated on DRAM banks of other PIM cores. And we have many PIM devices. So in total, this architecture provides around 2,000 PIM cores. These PIM-enabled memory modules are connected with a host system that is a CPU system, and we also have the common DRAM modules that are connected with the host CPU system, which is the standard DRAM memory modules. So in this system, we have developed a library that supports 25 SPMV kernels. We support many different compression formats, like the CSR and CUF are very famous, very widely used. We have many data partition techniques, load balancing scheme, and also different synchronization approaches. And in our work, we have a comprehensive analysis of this kernel on the first commercially available PIM system, the UPMEM system. And in the paper, we provide many recommendations for future PIM software system and hardware. So here is the execution of the SPMV kernel on a real PIM system. So the first step is that we need to load the vector of this kernel into the PIM-enabled memory modules, because the PIM-enabled memory modules are not integrated as a main memory for now. So we need to malloc the data on the standard main memory modules and then bring the vector to the PIM-enabled memory modules. Then the second step is to execute the SPMV by using the PIM cores. So the PIM cores provide a part of the larger SPMV that we need to execute, and they produce some partial results. And then we need to retrieve these partial results back to the host CPU, and the host CPU, we use the CPU cores in order to merge the partial results across the PIM cores and in order to get the final output matrix of the SPMV kernel and reconstruct the final output. So in this execution, I have omitted the load step for loading the sparse matrix in the PIM memory modules. I only include in the critical step, the critical execution, the loading the input vector. And this is because loading the sparse matrix is typically hidden in a real-world application as in the HPC domain. We typically load the matrix as a pre-processing step, and then we reuse the matrix in many iterations of the HPC application to execute the SPMV. So this part is not in the critical part. Okay, so then in order to execute the SPMV, we provide very different data partition techniques. One partition technique is like we horizontally partition the sparse matrix across multiple cores. So each core takes to process a subset of the rows of the full matrix. And then we have the 2D partition technique, where we create tiles, 2D tiles, and each tile is assigned to a PIM core. The number of tiles that we have on the sparse matrix is equal with the number of PIM cores that we have in our system. So this, with the first approach, we directly get the output of the SPMV. So the final output vector that we get is directly constructed on the PIM cores. We don't have any partial results. But with the 2D partitioning technique, we have partial results for the output that we need to merge them on the host CPU core. However, this technique provides a trade-off between computation and data transfers, because in the input vector, we have smaller data transfers for the input vector compared to the 1D partitioning technique, where in the 1D partitioning technique, we need to replicate the input vector at each PIM core. So in that example, we have 4 cores, and we need to have 4 replicas of the input vector in this case. And then for each the 1D partition technique, we have very different load balancing approaches depending on the compression format that we use. Here, I demonstrate how we can load balance the number of non-zero elements in a CSR and CUF format across 3 cores. In case of the CSR format, because the format is stored in a row order, we can load balance the rows across the cores, right? And in the case of the CUF format, we can load balance the non-zero elements across the cores because the format represents the data in a non-zero order. So here you can see that on the CUF format, the 4th row, it is partitioned across 2 different cores. Core 2 and core 3, they provide, they both work on the same row. And we have a near perfect non-zero element balance because in the CUF format, each core can have 3 non-zero elements. While in the CSR format, we don't have very good non-zero element balance because of the inherent representation of this format. Yeah, so then in the 2D partition technique, we have, again, we have tried very different load balancing schemes. In the first case, we have the equally sized tiles where the height and the width of the tile is equal across all PIM cores. And these techniques give us very high, it has very high non-zero element imbalance across the PIM cores because all the partitions and the 2D tiles that we create on the matrix, they are static tiles. They are just have a fixed height and width there. Then we have the equally wide tiles. In this technique, we have variable height and fixed width for the tiles. So we vary the height so that the core 1 and core 2 have almost the same number of non-zero elements to process. They have different number of rows, but because we just load balance the non-zeros there, they have high non-zero elements, non-zero element balance across the PIM cores that belong on the same vertical partition. And then in the last approach that we have tried, we have both variable height and width. So all the tiles are different between them, but we have very high non-zero element balance across all the PIM cores. So each tile each tile that is assigned to a particular PIM core has exactly the same number of non-zero elements as all other tiles, but they have variable height and width. So this creates like some imbalance on the input vector, on the width of the input vector, and the height of the output vector that we have for the partial result because of this approach. And yeah, so this architecture that we have, it also supports multi-threaded PIM cores. We have multiple threads within a PIM core. So even within the PIM core, we have tried many different load balancing schemes, either by load balancing the non-zero elements or the rows of the part of the matrix that is within one PIM core. And in some cases, because we have a multi-threaded execution and we have some a critical section there, we have some dependent data. We might also need to use synchronization and logs. So we have 3 different synchronization approaches to coordinate shared accesses on the multiple threads of the same PIM core. So in total, this library supports 25 SPMV kernels, including 1D partition techniques, 2D partition techniques, various compression formats, and synchronization approaches. And the library supports all different data types, including both integers and float and double precision data types. So we are using the UPMEM PIM system in order to do the evaluation, the performance evaluation of this library. In this system, we have around 2,000 PIM cores. Each PIM core has a 14-stage pipeline. It is a small in-order PIM core, and it supports 24 threads. And there is like a small cache that is called data. We call it data memory here. It is 64 kilobyte, and this cache is used in order to temporarily store some data and do some caching optimizations there. And yeah, each PIM core can access data only from its own local 64 megabyte DRAM bank. We have experimented with many different sparse matrices. We group the sparse matrices into families, the regular matrices and the scale-free matrices. In the regular matrices, the number of non-zero elements per row are similar across the rows. In the scale-free matrices, we have very high variability in terms of the non-zero elements per row that we have. You can see that one row has many non-zero elements, but there are many rows that they don't have any non-zero element there. So these are like called scale-free matrices or power law. They have a power law distribution, and they are very frequent basically in social networks. Okay, so first I will present a few results by looking only at the execution on the steps 2 of the execution, which is basically whenever we perform the SPMV on the PIM cores. So here we group the performance for the regular and the scale-free matrices, and we have the 1D partition technique, and we have the formats that I mentioned, the CSR-Q and BCSR-BQ are similar formats with the CSR and the Q, but they are like block-based formats. So what we observe here is that in case of the the Q and the BQ format, in the scale-free matrices, the Q and the BQ format are much better in terms of the performance compared to the CSR and the BCSR format. And this is because in the Q and BQ formats, we have almost perfect non-zero element balance across the cores because we can partition one row across two different cores, and each core can have almost the same number of non-zero elements with the other PIM core that we have on the system. And this is very important for the scale-free matrices, that they have this very high variability. And yeah, that's why Q and BQ formats are much better compared to the CSR and BCSR formats in this case. So the key takeaway of these results is that the compressed matrix format that we use to represent the matrix, it affects the data partitioning of the data across the PIM cores. And this data partitioning affects the load balance across the PIM cores, and we have the corresponding performance implications. So in order to improve this, we basically need to choose the compression format based on the data partitioning and the compute balance, the load balance that it provides across the PIM cores. In CPUs, that there is like no this kind of partitioning because there is shared memory. The Q format performs very well even in the scale-free matrices. But in the PIM architecture, because the Q format affects the data partitioning across the PIM cores, it has much better performance compared to the CSR format. Okay, so next I will present some results related with the end-to-end execution performance, including all the steps that I explained, both the step that we have to load the vector and retrieve the partial results, that also it is on the critical path of the execution time. Okay, so here we have all the different approaches that we used, the 1D partition techniques and the three different 2D partition techniques that we tried. And we observed that for the 1D partition technique, most of the execution time is spent on loading the input vector. This dominates the performance, and we are limited by this part. And this because in the 1D partition technique, the input vector needs to be replicated at each PIM core of the system. So if we have 2,000 PIM cores, we need to replicate the input vector at 2,000 PIM cores. So the amount of bytes that we need to transfer from the standard main memory to the PIM memory modules is linear with the number of PIM cores. And this is like a very large number of bytes. And this dominates the performance. Yeah, so the key takeaway is that here we need to replicate the same input vector at all the PIM cores of the system. So we use a broadcast collective to replicate this part. And this broadcast collective transfers data through the narrow off-chip memory bus, the memory bus that connects the PIM memory modules with the host CPU. So our recommendation is that we need to optimize the broadcast collective and design a broadcast collective to copy the same data, the same input data to multiple DRAM banks on the PIM system. If we take a look at the second scheme, that is the 2D equally sized scheme, we can see that the most of the time is spent on the kernel time. This is the time, the part of the execution time that dominates the performance. And this because in the equally sized scheme, we have a fixed static width and height in the 2D tiles of the matrix that we have. And we have a very high non-zero element balance across the PIM cores. So the execution is typically limited by only one or a few PIM cores that take to process the largest amount of non-zero element to perform the most of the multiplication on the kernel. Yeah, so the performance is limited by only one PIM core that has the largest number of non-zero elements to process. And then if we take a look at the last two schemes, the 2D equally wide scheme and the 2D variable size scheme, we see that here the retrieve time dominates the execution time. Most of the time is spent on the part that we need to get data from the PIM memory modules to the host CPU. And this is because in order to retrieve data from multiple PIM memory banks to the host CPU, the amount of data per core needs to be equal across all the PIM cores. So this means that in some cores, we need to perform padding with some 0 bytes, like some dummy empty data, in order to have equally sized partitions that we transfer from the PIM memory modules to the host CPU. And in this case, the 0 bytes, the padding that we do is like around 88% of the data. So most of the data are actually zeros there. Yeah, so the key takeaway is that in order to implement these schemes efficiently, we need to eliminate this 0 padding. We need to enable a collective, gather collective that we can get different sized PIM. We can transfer data with different sizes per core from the PIM and memory modules to the host CPU. So if we eliminate this 88% of the padding, this will give us a lot of performance improvement. Yeah, so our suggestion and recommendation here is that we need to enable a very optimized gather collective at DRAM bank granularity, where we transfer data from the PIM-enabled memory to the host CPU without having any 0 padding. We just need to transfer the data that we actually need to transfer. And finally, if we were trying to compare all the different data partition techniques that I have shown, and we use both regular and scale-free matrices, and we use a system that it has up to 2,528 PIM cores. In these experiments, basically, we vary the number of PIM cores, and for each matrix, we keep the execution time that gives us the best performance. It gives us the lowest execution time, right? We don't necessarily need to use the maximum number of PIM cores. We just do a brute force, and we just get the execution time that is lowest across all the different executions that we have collected. So in order to, here we have 2 observations. First, that in the regular matrices, we can see that the 2D partition technique provides better performance, while in the scale-free matrices, the 1D partition technique provides better performance because it provides better load balance across the PIM cores. However, we note that in all the matrices and all the executions, the best performance is achieved by using a much smaller number of PIM cores. In the regular matrices, we basically get the lowest execution time whenever we use around 1,000 PIM cores. And the other 1,000 PIM cores of the system, they are idle, they are not used. And in the scale-free matrices, the smallest execution time, the best performance we get is whenever we use only around 256 PIM cores, and the other 2,000 idle PIM cores are not basically used. And the smallest execution time is achieved because it's achieved using a small number of PIM cores, because if we use a very large number of PIM cores, we have very large amount of data transfers that we need to perform in the load and the retrieve part. So the best performing execution time is a trade-off between computation and data transfer costs. So eventually, although we have many cores, we don't necessarily need to use all of them in order to get the best performing execution time. Yeah, so eventually the key takeaway here is that if we manage to create, the data transfers are very expensive whenever we transfer data from an PIM-enabled memory module. And if we manage to improve this data transfers part, we will be able to fully utilize the available PIM devices and all the available PIM cores that we have in our system. Right now, we cannot fully utilize them and get very good performance with all of them because of the data transfer costs. Yeah, so our recommendation is that we need to design high-speed communication channels and optimize libraries for the broadcast and the gather collectives on PIM-enabled memory modules. We can also design system and hardware support to effectively overlap the computation on the PIM cores with the data transfers to the PIM memory modules, because right now they are not overlapped like as it happens in common multi-GPU systems. Whenever we do a transfer, we cannot use the PIM cores to do computations. This is not supported. And yeah, finally, we can also integrate the PIM-enabled memory modules as the main memory of the system. If this happens, we can just allocate data directly on the PIM-enabled memory modules. So we can just do malloc and write the data directly on the PIM memory modules and not using the standard main memory that we are using right now. So this will completely eliminate the load data transfers, the load step that I saw in the beginning of the execution time. Yeah, we compare also the SPMV execution with different commodity systems. Here is the real PIM system execution, and we compare it with a CPU system, and with a GPU system. For a fair comparison with the GPU system, we also, in the GPU case, we also account for the time to load the input vector from the CPU memory to the GPU main memory, and then the time to retrieve the final vector from the GPU device back to the host CPU. So if we compare this real PIM system with CPU and GPU devices, here I demonstrate the characteristics of the different devices, the different systems. Yeah, you can see that the CPU and the GPU are like basically processor-centric systems, where we have a very high peak performance, compute performance, and a number of operations per second that are executed, and we have relatively smaller memory bandwidth. And yeah, the PIM system is a memory-centric system where we have a very small compute throughput, compute capabilities, but we have a very large aggregate memory bandwidth available on the system. So if we compare these different types of systems on the SPMV execution, we can see that in the PIM system, we have a much larger utilization, resource utilization. With the PIM execution, we achieve like 50% of the peak performance that is supported on the PIM system. However, in the CPU and the GPU system, the utilization is basically less than 1%, right? So this means that, you know, we just buy a GPU or a CPU, we pay a lot of money, but we don't utilize it. We don't compromise this execution time because we only get 1% of the utilization of this device. However, in the PIM case, we have around 50% of the utilization. So it is more a cost-effective solution for this kernel. Yeah, so if we take a look at the actual execution time and the end-to-end performance, we see that the CPU performance is the best one. And this because there are no data transfers. Even in the GPU case, we have some data transfers. And in the PIM case, we have very low execution time because of the larger amount of data transfers that we have. So the absolute execution time still the PIM system, it lags behind, is much worse compared to the CPU and the GPU. And yeah, we have more results on the paper, and we also evaluate the energy consumption there. So before I go to the second part, I'm happy to stop here and get some burning questions, or if you guys have any questions. Which? Yeah, there are around, I think, 20 PIM DIMMs on the system and 10 PIM DIMMs, around 10 PIM DIMMs for the DRAM memory modules. No, we only support, we only evaluate the UPMEM PIM system right now in this, in this library. The data partitioning techniques that we propose can apply also in HBM PIM devices. Yeah, sure. I can go back to those slides. Yeah, so the difference between the equally wide and the variable, these are like similar schemes. They have like similar performance and execution time. Both of them are basically target to improve the non-zero element balance across the PIM cores. In the equally wide tiles, we have high non-zero element balance across the PIM cores of the same vertical partition, only the PIM cores that belong on the same vertical partition. While in the variable size schemes, we have high non-zero element balance across all the PIM cores of the system, both within the vertical partition and across the vertical partitions. Yeah, but the performance results that we demonstrate that we have collected, they show that these schemes are basically they achieve the similar performance. So even the equally wide scheme has like a good non-zero element balance by default. Yeah. Yeah, sure. Yeah, so that's a good question. We have all these results in the paper. I mean, still the energy consumption is very expensive on the PIM system. It is worse compared to the CPU and the GPU because the execution time is worse, and also the energy consumption is worse because the energy is correlated with the execution time, right? And these PIM devices, it is the first product, the first generation product of UPMEM. So even the technology node and the manufacturing process is it's not mature enough. So the power consumption is quite high. Yes, we leverage the whole bandwidth and we achieve very high resource utilization in the system. Yeah, but yeah, we expect that next generation PIM systems will be improved in terms of the energy aspect. So I expect this will change in the near future, hopefully. So this library is designed in order to support many different applications and many different matrices that they have like different kind of distribution of the data. So in order to find which distribution is like the best one for each application or for each matrix, we need to tune and choose the correct SPMV implementation for the library that we have. Yeah, so in this project, yes, we assume. In the next project that I will present next, we have automated this part. Okay, so let me then move to the next project, and I can get more questions at the end of the talk. Sure, I will try to. Yeah, so yeah, in this project, we basically create a framework to deploy graph neural networks on real PIM systems, and graph neural networks are very widely used and very important. So they have multiple GNN layers. Each GNN layer has two steps, the aggregation and the combination. The aggregation step is a sparse matrix multiplication, and the combination is typically a small neural network that has dense matrix multiplications. So if whenever we profile this GNN execution, the GNN layer, we find that the aggregation part, which is the sparse matrix kernel, it is highly bandwidth by the memory bandwidth, even with a GPU with a very large available memory bandwidth, 3090. This part is like takes most of the execution time, of most of the inference time, and it has very low core utilization, low resource utilization. Yeah, so we basically map the aggregation step on the PIM memory systems, and we have created a GNN framework that runs the aggregation step on the PIM system, and it runs the combination step on the host system that is typically CPU or GPU. And it has 4 key techniques that I will briefly describe next. Yeah, so the first key technique is that we have a cooperative acceleration execution where the combination part is the compute bound and it is run on the host system that is typically either CPU or a GPU system. And the aggregation part is a sparse matrix multiplication kernel, and we have optimized it and run this part on the PIM-enabled memory modules. So this is like the execution for each graph neural network layer, and we have many layers. Yeah, so the second key idea is that we have a combination of parallelization techniques. We group the PIM cores in cluster, and across PIM cluster, we perform feature and edge level parallelism. Then within the PIM cluster, we have many cores, and we perform vertex and edge level parallelism. And then within the PIM core, we have multiple threads, and we perform vertex and edge level parallelization approaches. So the key idea is that we don't have only one parallelization scheme. We only balance non-zero elements. We only balance non-zero rows of the matrix, but we have very different, we have 3 types of parallelization schemes by doing this like multi-level parallelization approach. And this optimizes the performance a lot. Yeah, because basically with this approach, we can strive a balance between computation and data transfer cores on PIM devices. And we can also support many real-world graphs or matrices that they have very different characteristics in terms of the non-zero element distribution. Yeah, so in order to find which is the most appropriate and best performing parallelization approach to use, how to balance the non-zero elements across the clusters, within the cluster and across the threads of the same PIM core, we have designed a tuning system that it profiles the real-world graph. It profiles the real PIM system in order to collect the peak performance of the system and the bandwidth that is available. And it uses some performance model. And based on this performance model, we can find the correct parallelization strategy that we are going to use in this library, in this framework. So eventually, we have designed a Python interface because typically we employ machine learning models using a Python interface, where the programmer basically just needs to import the PyGym, our framework there. Then in the forward pass, instead of like running the aggregation part on the CPU, the user needs to use our PyGym framework in order to run the aggregation kernel on the PIM side. So it is basically just a small API that we need to integrate in our source code. And then finally, before we create the GNN model, we need to use the tuner. So the tuner is like a small pre-processing step that we perform in order to find which is the best performing parallelization strategy in our PyGym framework. And after this tuner runs only once. And then after we run the tuner, the user can create any graph neural network model. Here, I have a graph neural network model that has three layers, basically, 1 linear and then 3 convolutional layers. And the forward pass, the inference is hybridly executed between the host CPU and the real PIM devices. Yeah, so here we compare with PyTorch, the default and optimized implementation of PyTorch on the CPU. And then we have many different baselines, the Sparse P that I explained before. The grant is a prior PIM work that was proposed in the literature. And then for the PyGym, we have both CSR and Q. Yeah, over these baselines, basically, PyGym performs significant performance benefits. On average, it is around 3x better over CPU and prior, more than 3x better compared to the prior CPU and PIM-based schemes. And similarly for the energy efficiency, again, here we have the same baselines as before. Here I saw energy consumption, so lower is better. Yeah, on the x-axis, we have many graph neural network models. We have 3 different models and 3 different data sets. So in average, we have much better PyGym is more energy efficient compared to the PyTorch CPU and the other PIM-based works that exist in the literature. yeah, so to conclude, yeah, sparse computational kernels are very important and widely used in many applications, but at the same time, they are memory bandwidth bound. So real processing memory devices can tackle this data movement bottleneck, and they can expose very large aggregate memory bandwidth for those sparse kernels. However, the challenge is that real PIM systems are still in early stage and they have low-level programming interfaces. The software stack is not like very mature enough. So our contribution is to create the software stack for real PIM devices for those sparse kernels. And we propose Sparse P, an open source library for SPMV kernel, and PyGym, it's an open source graph neural network framework for real PIM devices. And in both our papers, we have many recommendations for future PIM hardware and software, how we can improve multiple levels of the stack in PIM devices. So yeah, thank you for your attention. Yeah. Yeah, I can get more questions if we have some time.
I'm curious, the first part of the talk, do you have a sense for something like Apple's M series chips, where you don't have to transfer, GPU and CPU share memory, so you do the transfer? Do you have a sense for the utilization?
Yeah, that's a good question. I mean, in our case, we have 50% utilization with data transfers including there. So if the data transfers is 0, I mean, it's hard to estimate a number, but it will be like close to, yeah. I'm not sure if it will be like 80 or 90, but I expect, yeah, it will be much better. Yeah, thanks.
This? Is it like this? Do we have clickers? Oh, okay. Let's go back. Okay. Okay. Yeah, sure. I introduced myself. Yeah. Hi, everyone. Do you hear me? Okay, perfect. So I'm Nika. I'm going to talk today about storage-centric computing for genomics and metagenomics. So we will basically talk a little bit about near data processing inside the storage with these use cases in genomics and metagenomics. And I will provide some background about these specific applications. So a bit of introduction. I am Nika, PhD student at Safari Research Group. I work also with Professor Mutlu. And my research interests are in computer architecture, large-scale bioinformatics applications, storage system, near data processing, and emerging technologies. And here's my contact information if you'd like to stay in touch, or we can also talk in the conference. Here's a brief outline of my talk. So I will quickly talk about metagenomics and genomics. So no prior background is needed here. I'll provide whatever is going to be needed. I will talk about some of the work we've been doing into designing storage-centric systems for these data-intensive applications. And then I will conclude. So genomics and metagenomics are critical for many different applications, such as personalized medicine, and understanding microbial diversity of environments, and preventing and detecting disease outbreaks, and in general, understanding the genetic variations in a population. So they have these all broad applications, and at the end of the day, we want to see the DNA of the organisms and how they work, and how they differ from case to case, and based on that have medical or biological understandings. So this is a set of DNA nucleotides that we want to work with. And based on similarities and differences in these DNA molecules of different organisms, we would be able to have different conclusions or studies. So to get these sequences, we have these genome sequencers that receive the molecules, DNA molecules of the samples, and then translate them into these characters. And there's been a lot of advancements recently into making these things high throughput and low cost over the past few years. So the issue that we have in high level right now is that we have these specialized, really fast, high throughput systems that can generate data at low cost, but then relying on conventional systems to analyze this data is very challenging and leads to very slow analysis. So why this problem exists in very high level, if I simply want to explain, is that these applications typically require performing expensive computation on large amounts of data. So because of the importance of this domain in many different critical applications, so then we have, computation overhead and data movement overhead. So because of the importance of these domains, there's been a lot of effort into accelerating them by devising efficient heuristics, efficient types of filters to filter data that does not require expensive computation, and hardware acceleration. And actually, even in industry, there's been a lot of effort over the past few years, and the efforts are increasing in industry also to accelerate these things. That's been nice. And these techniques led to significant alleviation of computation overhead. But the data movement overhead from storage system to the rest of the system still exists. And its impact actually on end-to-end performance becomes even larger when other bottlenecks such as computation and main memory overhead get alleviated. So that is why in our work, we've decided to look into some storage-centric solutions for these applications. So what is metagenomics? Metagenomics is a study of genome sequences of diverse organisms within a shared environment, such as, let's say, a patient's blood sample or gut or body of water, let's say in oceans or soil. So in some cases, all these organisms are together in this shared environment, and being able to analyze everything in this shared environment together in a metagenomic fashion, let's say, overcomes limitation of traditional genomics, because for some cases, it would not be possible to separately analyze these species in the lab. So all these benefits exist, but then since we don't know, in many cases, what are the species in the sample, metagenomic analysis requires first figuring out what is in the sample, and that needs looking up a large database containing information on many species. And these can actually be very large, more than 100 terabytes in some of the recent examples. So anyway, the amount of data we need to work with in metagenomics can be even much larger than the context of genomics. So, motivated by these points, we have been looking into several storage-centric designs for these applications. I will very briefly talk about two of the designs that we have worked on. And of course, I'll be happy to chat about you later about other things going on. So the first one is called GenStore, a high-performance in-storage processing system for genome sequence analysis. So if you, so we discussed these are the benefits. So this is the DNA molecule. So the sequencer machine, so this is my drawing of one of the machines, let's say, they cannot read the whole DNA molecule at once because they can be really large sequences. So they typically read these smaller fragments that are called reads. So when doing genome sequence analysis, one of the first things we need to do is to map these reads to some reference genome. So that's a process called read mapping. So that we can find the potential matching locations of these reads. And also for each matching location, we want to perform this alignment step that finds the similarities or degree of similarity or alignment score of each read to the reference genome. And then differences can happen due to sequencing errors or genetic variation. So it's really important to analyze these differences, but then finding them is really expensive because it requires the computationally expensive approximate string matching. And as we discussed, we need to perform this expensive computation on a really large amount of data. So what we do actually here, so this is a diagram we saw before. So what we do here in GenStore is that we filter the reads that do not require the expensive computation right inside the storage system with some lightweight structures. So then we can only send whatever data needs to go to expensive computation outside the SSD. So that helps fundamentally reducing data movement overhead and in general overhead of this filtering operation throughout the whole system. So there are some examples of these reads that can be filtered inside the SSD, exact matching reads or non-matching reads. We will talk about them in a little bit more detail in the later slides. So despite all these benefits, it's very challenging actually to get this implemented inside the storage system. That is because these read mapping workloads can have different behavior based on genetic content that is in the sample. So what type of read can actually be filtered depends on what organism we are comparing to what reference genome, etc. And also there are hardware limitations inside the storage system. So we do not have as much, let's say, high bandwidth DRAM that we would have, let's say, in a conventional system to work with. So here the limitations are even much higher than what would exist outside the SSD. So we have these limited resources to work with. So we address these challenges as we will see in the slides and in GenStore to alleviate computation overheads and data movement overheads. And we show that we can get actually significant speed up and energy reduction at low cost. So this is a very high level overview of what GenStore is going to do. So we will go through more details. So that's going to be the outline. I will talk about the background a little bit in more detail, what read mapping does before we dive into the design of some parts of GenStore. So this is a reference genome that we talked about, and then that's one read. So for example, let's now try to map this one read to see how it works. A read set can have several millions of reads. So anyway, the search space for this reference genome can be very large. Let's say for humans, it is more than 3 billion characters. So it's very difficult to search it. So now we have index structures that can be typically built offline. That is going to encode some k-mers. K-mer basically means subsequences of length k. These are extracted from the reference genome, and then the locations that they happen to occur in the reference genome, right? So, okay, a typical a typical read mapper typically generally has these 3 key steps that we will talk about in high level. First step is to do seeding. So determine some potential matching locations or seeds in the reference genome that we want to do this expensive approximate string matching or alignment step up. So how do we do that? So we extract also some k-mers from the read. We look it up in this reference index and find some potential locations. So we call these things seeds. The second step is seed filtering or chaining that prunes the seeds that are unlikely to be useful in the reference genome. So here we prune these ones. So this is typically requires some more lightweight computation compared to the alignment step. So if a read does not have any remaining location, it gets fully pruned. Otherwise, the reads that have any remaining location, they go to the third step, which is the expensive alignment step that determines the exact similarities or differences between the read and the reference genome at these matching location. So that's kind of like all the genomic background we need for the rest of the talk, hopefully. Oh, sorry, this is a redundant copy. We go here. Okay, cool. So let me show you the potential benefits of ideal in storage filter. So we did some case studies to see what are the real world genomic datasets on various read mapping systems, both in software and hardware, with various state-of-the-art SSD configurations, some of them optimized for cost, some of them optimized for performance. And what we generally observed is that an ideal in storage filter, forget about all the hardware constraints. So if we could filter all the reads that we could potentially filter with 0, let's say, performance overhead, it can significantly improve performance by reducing computation overhead and reducing data movement overhead from storage system. But then we also try to look into having an ideal filter that again would at 0 seconds filter all the reads that do not need to go through, let's say, the alignment step outside the storage system. And what we observed is that it does not reduce the data, it does not provide as much significant benefit as an ideal in-storage filter, because of course it does not address the IO overhead. And also must compete with read mapping for system resources, meaning for main memory bandwidth and computation units, it takes away those resources that could otherwise be used for full read mapping of the unfiltered reads. So these are the two reasons that that ideal filter outside the SSD does not provide as much benefits. And also what we observe is that a hardware accelerator reduces the computation bottleneck of read mapping. So even a processing memory or other types of read mapping accelerators help address computation and main memory bottlenecks in different ways. But then in those systems, the impact of bringing data from a storage system becomes even larger. So IO becomes even a more important problem in their end-to-end performance. So motivated by these points, our goal in this work has been to design a storage filter for genome sequence analysis in a cost-effective manner. And we had 3 design objectives. The first one is to have high performance so that we can fully hide the performance of filtering that is happening inside the SSD with the read mapping process of unfiltered reads that happens outside. And the second point is the applicability to support be able to support reads with different properties and different genetic variation and have low cost. So I go through the design of GenStore in high level. So the key idea is to filter reads that do not require alignment inside the storage system. So we put some accelerators on the SSD controller. And whenever there is a read that does not get filtered, it can immediately get sent to the host system or any other genomic accelerator for more process. And the challenge, as we discussed, is different behavior across read mapping workloads and limited hardware resources in the SSD. So let's take a look at filtering opportunities in more detail. To do that, we need to understand what are the behaviors of these sequencing machines. So I'll show you a lot of examples in some of the earlier slides, but overall, they generate 2 types of data in high level. One of the short reads that are highly accurate, but their length is relatively smaller. And the other one is long reads that are less accurate relatively, but their length is much larger. And each of them have different trade-offs and use cases. So let's see that what would be the reads that do not require that expensive alignment step are exactly matching reads because they do not need approximate string matching. They just are exactly matching. And they can happen in reads that have low sequencing error rates, I mean short reads, and low genetic variation. For example, us humans have very low genetic variation. We are like, in a human read sample, around 80% would exactly match. Even we are kind of like close to, genetically, we're close to bananas with like 50%, something like that. So this is, as I said, this exact matching case is particularly very useful for human case. And then we have non-matching reads that are reads that do not have any potential matching location. So in the second step of read mapping that we talked about, nothing remains to go to the third step. So that will be reads with high sequencing error rates or high degree of genetic variation. For example, virus or bacterial sample, they have very high degree of genetic variation. Okay, so then we have 2 designs here, GenStore EM for exactly matching reads and GenStore NM for non-matching reads. For the sake of time today, I will only actually talk about GenStore EM in this work. But if you're interested, please check our paper for GenStore NM details. So GenStore EM is an efficient in-storage filter for reads with at least 1 exact matching location in the reference genome. And it uses only simple operations without requiring alignment. But the challenge is that we have a large number of random accesses per read to the reference genome and its index. And this causes issues because it is relatively more expensive to have these random accesses on to the NAND flash chips, which is the prominent technology used in modern SSDs. And then we have limited DRAM capacity also in the SSD. For every terabyte of storage, we have only 1 gigabyte of DRAM. So for like, let's say, a typical SSD, all that reference and index might not fit into the DRAM inside the SSD. So in general, it's very difficult to handle these random accesses for each single read. So this is the ideas we have to work around that. So I hope that this provides an example that how hardware and software need to work together to enable something, because this algorithmic optimization we see here is kind of very different from what it would be beneficial necessarily outside the storage system. So anyway, this is the read, and then typically conventional read mappers extract k-mers out of it, as we discussed, to look up in the index and then later in the reference genome, right? So to reduce the number of random accesses, what we do is that we introduce the concept of read-sized k-mers. So we look at the whole read as one single k-mer. So this now for this figure, I'm showing a small k-mer, but in reality, this can be a short read around 100, 150 characters, right? So it's a pretty long k-mer in this case. So we have only one index lookup per read. And since we have one access per read, then we have the luxury of being able to pre-source these read-sized k-mers, so that we can avoid random accesses to the index. So that leads to being able to finding these exact matches with only sequential access of the read set and the index. So let's see how it works in a simple example. So this is a read. As I said, in reality, this can be 100 plus characters. And then we have sorted read tables, so read and read IDs. And then we have sorted k-mer index. It is similar to the k-mer index we talked about earlier, but it is for these really large k-mers. So let's say if typically in conventional applications, these k-mers are 15 or 19 characters. This can be like 100 length, let's say k-mers, 100 mer in a sense, right? So it's a larger table. But then again, in the other column, we have locations of these k-mers in the reference genome. And as we said, both of them are sorted. So finding exact matches in this becomes really simple, right? So we have only this comparator. If they're equal, okay, good. They don't need to go through any further processing. They get filtered inside the SSD. Then we go to the next elements. If read is bigger than the k-mer, we go check the next k-mer. Okay, and now the k-mer got bigger than the read. So we realize that the read did not match any k-mer, right? Because we're sequentially scanning everything. So that is not an exact match, and it needs to go to the read mapper to be further analyzed. So and that's the good thing about it, that these, as soon as something gets detected, can be sent out for further analysis. And then we go to the next read. So then this avoids random accesses and enables us to find all of this with only a simple comparator, right? But then the size of the data increases, of course, because we have larger k-mers and therefore more unique k-mers. When the k-mer size increases, so we reduce the size of this table by replacing these k-mers with the strong hash values that represent these k-mers. And so this leads to around 4 times reduction of the size of this table. However, it is still larger than the index table that was used in the baseline read mapper. But it helps filtering all these reads with very efficient access patterns, right? So therefore, we figure out that this is a more suitable trade-off for the context of in-storage processing. Okay, and these are the tables, the sorted read table and the sorted k-mer index. They are distributed evenly across different channels, so we can have full leverage, like full benefit of SSD's internal bandwidth and this simple hardware logic that reads data in batches sequentially and sends the whatever that does not get filtered to the host system. And then these steps are pipelined, and therefore filtering can be overlapped with read mapping. And as I said, further discussion of GenStore NM would be in the paper. Let's take a look at some of the results very quickly. So these are some read mappers as the baseline. So there are both software and hardware read mappers for short and long reads. And one of them is also a near data processing accelerator already. And GS is integrated with GenStore. So it is important to see that GenStore gets combined with these read mappers to augment them further, right? So you can use a processing memory accelerator or a different type of accelerator to do other parts of the read mapping. But this GenStore enabled SSD can just be combined with them orthogonally to increase their benefits in a sense. And then we have different SSD configurations that we analyze. So here I'm showing benefits of GenStore EM. So compared to software and hardware baselines, and we see that it provides large benefits across different types of SSD configurations and with large energy reduction. And then we also see here benefits of GenStore NM. So we don't discuss the design, but then for me to quickly summarize the results. So here we compared also against software mappers and hardware mappers. So it's not comparing against, it's to show how much it helps increasing their performance benefit. So it leads to substantial increase in their potential performance and with large energy reduction. There are many more results also in the paper, so please check if you're interested. And also we can chat, of course, afterwards. So that was summary of this work. I will also quickly talk about the other work. But before I move, are there other questions? Okay, then maybe I can just go to the next one. Okay, so this one is about metagenomics. So it's a high performance, energy efficient, and low cost metagenomic analysis in storage processing. So we talked already about in high level what metagenomic is, but let me talk a little bit more detail into the steps involved in it. So metagenomic sample that we talked about, there are some species that we do not know what they are in advance. So these are the DNA sequences, so we need to do 3 steps. First is to prepare these input queries. So we extract these shorter sequences, these k-mers out of them, and we then need to figure out what is in the sample. To do so, we look at these extracted k-mers into a large database that contains information on many different species. As we discussed, it can be very large. So after that, we figure out, okay, these are some organisms that are in the sample, and there's this third potential optional step that some analysis tools would perform, which is abundance estimation, that finds the relative frequencies of these organisms in the sample. So because metagenomic analysis requires accessing very large amounts of data, we perform a case study of impact of I/O overhead on performance. So compared to an idealized case with no I/O overhead, we show that for both performance optimized and cost optimized SSDs, I/O data movement causes significant performance overhead and end-to-end performance. And similarly, we also observe that when I/O becomes even larger overhead in systems where other bottlenecks such as main memory and computation get alleviated. So I/O overhead due to accessing this large amounts of low reuse data is very hard to avoid. One might think it might be possible to avoid it with some sampling techniques to shrink the database size, and actually in the context of, let's say, pure genomics or metagenomic software tools that has been investigated, but that leads to reducing accuracy to levels that would be unacceptable to many use cases. And another case would be to keep all data required by metagenomics completely and always in main memory. Right, so for example, with developments of CXL memory expanders, one might think that, okay, so can I have this very large memory and keep this data always there so that I can work around my I/O overhead? But such solutions for this context would be inefficient, costly, unscalable, and unsustainable. And that is because of 2 reasons. One is that these database sizes increase in size very rapidly. So already they are very large, but then they double every few months. And the other point is that regardless of individual database sizes, different analysis require accessing different databases. So it doesn't make sense to keep all possible databases that different types of analysis need completely and always in memory. So motivated by these points, our goal in this work is to improve metagenomic analysis performance by reducing data movement overhead from storage system in a cost-effective manner with high accuracy, because this high accuracy is actually critical for many applications in precision medicine. So, but then again, doing it is difficult, although we can have, again, this processing units inside the SSD, but doing it is very difficult in this context because no metagenomic analysis tool can directly be used there and be mapped in this context because of large latency of NAND flash chips, small capacity of DRAM that we have inside the SSD, and it's very small bandwidth. So in this work, we try to address these challenges and design Megis, which is the first storage system for end-to-end metagenomic analysis. And the idea is to enable cooperative in-storage processing for metagenomics that is enabled by hardware-software co-design between the storage system and the host system. And these are the high-level overview of the steps. So we already looked at these. So this will be Megis as a step 1, and step 2, and step 3. So for Megis, I will not go through its detailed design, but I still would like to talk about some of the aspects of hardware software co-design that were involved in these different steps to actually be able to leverage both host system and SSD to work together efficiently. So the first one, of course, is to partition the application between different systems, between host system and the Megis-enabled SSD. And the second, so yeah, these are the steps get mapped here. So if you're interested into the reasons why this mapping happened, I would again invite you to check the paper. The second point, which is very critical, is to handle data and computation flow between the two systems. So we are taking advantage of capabilities of both systems, but it is very important that data movement that we cause between these two systems actually does not basically reduce the benefits that we can get from them. And also to reduce the number of writes to NAND flash chips, because the host system needs to also send back some of its data to the SSD. So we need to ensure that we do not increase the number of writes to the SSD in this case. And the third point is the storage-aware algorithms that would enable efficient access patterns to the SSD. So we saw an example of it in the context of GenStore. In this case, also, there are different algorithms that, again, we had to revisit them through different mechanisms and approaches, but to make the access patterns more effective for in-storage processing context. And a lightweight accelerator so that we can minimize the amount of SRAM and DRAM buffer spaces that we would need. And finally is data mapping scheme and flash translation layer that get optimized specifically based on features of metagenomic analysis. So these are some of the aspects that need to all work together to enable this design. Again, because of sake of time, we will not go through them in detail, but I still would like to highlight what gets enabled by having these storage-centric designs. So this is one of the results that I would like to highlight. So consider two systems. One of them is a cost-optimized system, which has a cost-optimized SSD. So here is a SATA SSD in this case with lower bandwidth, with 64 GB of DRAM. And then consider a performance-optimized system that has SSD performance-optimized SSDP, which is a PCIe Gen 4 SSD, has higher bandwidth compared to SSD-C, and 1 TB of DRAM. And this, for this example that I will show the data, the amount of data we will work with is around 700 GB, so it's smaller than the DRAM size, meaning it would fully fit, but then it has really low reuse, right? It still needs to come from storage system to DRAM in this case. But DRAM is already very large. And that 700 gig would not fit in that smaller system, DRAM, right? And what we show is that so these different applications, different baselines, there's a performance optimized software tool and accuracy optimized software tool. So the performance optimized one has a smaller database, so works with a smaller amount of data, but has lower accuracy compared to this accuracy optimized baseline. And then we run these systems on the more expensive system as well. And when comparing it to Megis running on a cheaper system, we see that, so when they run on the same system, we see large benefits, but then we also see that Megis outperforms these baselines even when running on a much less costly system, which shows the benefit that when being able to handle all those large amounts of data in the denser storage structure, one would be able to kind of enable these data-intensive applications in, let's say, even a portable system, right? That was the summary of this work. I put also the link to the archive version because it is longer than the IEEE version for ISCA, so it has more pages with more analysis and results if you're interested. So it's a very brief conclusion also. So specializing the storage system for genomics and metagenomics can provide large benefits. So these storage-centric designs improve system cost efficiency, as we discussed, and then we hope that it would make these accurate genomics and metagenomics applications more accessible for wider adoption, because as we discussed over the past few years, the cost of sequencing the data and the throughput at which we can do it has dropped significantly. So this should not anymore be like a luxury application for like selected or few sets of people. So we really hope that this being able to handle the computation overheads and data movement overheads efficiently in such storage-centric designs, be able to make it more accessible for the wider adoption. And yeah, so as we discussed also, this co-optimizing algorithm and architecture and device, all of them are critical, so all of them are bounded together. So this is, I think Geraldo might have shown this already, yes. So this whole stack of computer architecture. So we saw how algorithm had to change in optimizations, which were different how we would optimize the CPU in the context of storage processing. And so I also had the chance to collaborate with other people in my group on different parts of this stack. So this is a summary of other directions I'm interested in, and also my website. And I'd be happy to chat with you in the conference about any of these. Yeah, thanks. Sure.
And you are running out of time, so we have two plans.
Oh, nice to meet you, Koji. Okay. Thank you so much.
So what kind of this simulator you are using?
Well, we are using MQSim, and for the computation part, actually, would you like to take it outside if you prefer? Yes. See? For the parts that and the part so, and then we
See, oh, that's
what topics do you work on?
actually I was a generation of micro 2018
Oh,
in Japan,
wow.
and recently I'm working for the
Okay. Okay, and do you still require the low temperatures or
yeah, 4 Kelvin.
okay,
It's
okay.
only low.
Oh, okay. Do you work on real systems as well?
Actually, we can fabricate the chip.
Oh, okay.
Yeah, but actually it's a process technology is really, really huge.
I
So
see.
Okay, so sorry once again for the delay. And we are going to shift gears. We keep talking about processing near memory. So we talk about processing near SRAM, and we talk about processing near DRAM, and we talk about processing near the storage, right? Now you're going to shift to processing using memory. And as a reminder, in processing using memory, you're not going to add any logic to do computation. You're going to use the memory cells themselves, to perform some sort of computation. We are going to build over time as the complexity progresses. Operations are going to become more and more complex, but you're going to start really simple. You're going to start with some simple data manipulation operations. So data manipulation operations like data copy and data initialization is really important in many different applications and different application domains. So operating systems, for example, do zero copying, checkpointing, or forking, which involves such operations. So there is some study from Google, for example, that shows that aggregated across all of the data, all of the computers in the data centers from Google, they saw that main copy and the main move spends in total 5% of the execution cycles of those applications, which might sound small, but actually it's quite a big number because you are aggregating across all of those data centers. So in current systems, how you actually do those operations, how you move data around, right? So what you do if you want to copy one page in DRAM to another page in DRAM in conventional systems is that you move cache line by cache line of the source page into the CPU. And then you move the cache line from the destination page again to the caches to the CPU. Then you do the data copy, and then you write back the result, cache line by cache line. So this operation is quite high latency intensive because you need to move one cache line at a time from the main memory to the memory bus and to the caches and to the eventually the CPU. They consume a lot of bandwidth because you need to move again those cache lines for both source and destination arrays. They create cache pollution because the only operation that you do is basically copy one cache line to another, and also they generate unwanted data movement. So as an example, if you do this operation without involving the caches, just doing via DMA, the latency that it takes to copy a page is of around 1,046 nanoseconds, and the energy that consumes is around 3.6 microjoule. So what we want instead of doing this is actually just tell my memory, copy the source data to destination data. Don't bother bringing anything to the CPU. Don't bother moving anything to the memory channel. So this enables you to do computation with low latency, low bandwidth utilization, no cache pollution, and no unwanted data movement. And as I'm going to show later on, if the system exists, you can reduce the latency of this 4 kilobytes data copy from this 1,000 nanoseconds to 90 nanoseconds, and the energy from 30.6 to 0.04 microjoule. Okay, but how you actually design the system, right? But before that, I'm going to bother you a little bit with some DRAM backgrounds. Otherwise, whatever I'm going to say next is going to look like is magic. So a DRAM, this is going to be the fastest DRAM background that you ever had in your life. So a DRAM chip is organized, a DRAM model is organized with a set of DRAM chips operating a lockstep in a rank. Inside the DRAM chip, you have a collection of what's called a DRAM bank. A DRAM bank is organized to the array of DRAM cells, which are horizontally connected to word lines and vertically connected to bit lines. So those bit lines are connected to a sense amplifier, and a group of the sense amplifier is called a row buffer. A DRAM cell itself is composed of a storage capacitor, which store data, and an access transistor, which connects the storage capacitor to the bit line and hence to the sense amplifier. To access a DRAM cell, the memory controller issues three main commands: activate, a read and write, and a precharge command. So first, when issuing the activate commands to a particular source DRAM row, what happens is that the word line is raised. This connects the storage capacitor to the bit line. Then the storage capacitor is going to lose its charge and generate some perturbational voltage deviation in the bit line. Then the sense amplifier is going to be enabled and it's going to sense this generated perturbation to the bit line to either a logic VDD or ground value. So after that, the data is in the storage capacitor is restored to its original value. So after that, the DRAM chip the memory controller can issue read and write commands to the data that was previously sensed and latched in the sense amplifier. After that is done, you need to prepare the DRAM chip for a follow-up request to a different DRAM row. And this is done by issuing a pre-charge comment. This basically lowers the word line, disconnecting the storage capacitor through the bit line. And then you pre-charge the bit line to its considered state, which is usually half VDD. And finally, we disable the sense amplifier. Going back to that in-DRAM row copy, we are going to use this in-DRAM activation operation, which already happens for you to access data, to do this in-DRAM copy inside the DRAM chip. So the way that works is quite simple. Instead of doing that sequence of operation that I just mentioned, activation, a read, and a pre-charge, we are going to issue two back-to-back activations to the DRAM chip. So what this does is, first, we activated the source row that you want to copy. This lets the data into the local buffer, exactly what I just mentioned in the background. But then we are going to issue a second activate to the destination row. This is basically going to connect the cells in the DRAM row to the bit lines and hence to the local sense amplifier, which now has the data from the source row that was just activated previously. So this copies the data on the latch on the sense amplifier to the now activated destination row, hence realizing the in-DRAM row copy operations using these two back-to-back activation operations. So this incurs basically no cost to the DRAM chip because basically we are just using the operating principles of the DRAM chip itself to realize this computation. The way that it works, again, just to illustration purpose, we will activate the source row, that DRAM, the target DRAM cell loses charge to the bit line, creating a perturbation. The data is latched to the sense amplifier. Then you send another activation to the destination row. The data is latched, and then it's going to be copied from the local sense amplifier to the bit line, and hence and finally to the destination row. So we call this mechanism Ambit, row clone, and then we saw in this row clone paper that we can significantly reduce the latency for in-DRAM row copy operations and the energy that it takes to copy data inside the DRAM chip quite significantly. So all of this is really nice. We can do those row copy operations efficiently, right? Just by violating the way that DRAM operates, but it's quite naive, right? Or primitive. You can only do this row copy operation. What else can I do? So following up on row clone, we have Ambit, which is going to use, again, the same analog operating principles of the DRAM chip itself to now do triple row a majority-based computation, so Boolean operations. The way that it works is quite similar to what I just mentioned for row clone, but here instead of activating 2 DRAM rows, we are going to activate 3 DRAM rows at the same time. So when you activate the 3 DRAM rows at the same time, those 3 DRAM cells connected to that row are going to simultaneously generate a perturbation, the local bit line. And since what we have as a sense amplifier is a differential circuitry, this sense amplifier is going to pull up the voltage level to the majority of the initial voltage levels stored in those 3 DRAM cells. So in this example here, the cells were 2 cells were charged, the other one was discharged. The majority of this is charged. So hence, by doing that, what the final states that we are going to have in the sense amplifier is going to be the majority of 3 of those 3 selected DRAM rows. And by controlling one of those inputs, like either by setting it to 1 or to 0, basically we can realize in-DRAM or in-DRAM AND operations. So, okay, we can do copy, we can do in-DRAM row or and AND, right? What is missing for us to be function complete is not. So the key idea for us to implement not is to leverage the fact that we already have a not already placed there in the sense amplifier. The design of the sense amplifier is basically 2 back-to-back inverters connected in a loop. So we are going to reroute one of the output of those one of those negated those inverters back to the cell. Hence, by controlling that new connection, we can do not operation as well in the DRAM chip, leveraging whatever the circuitry was already there. So we use this idea of Ambit to implement some Boolean operations. So now that we have majority, Boolean, and or not, we can implement other things like NAND and NOR and XOR and XNOR, and compare the throughput of those operations to a CPU and a GPU. We can see that we significantly improve the throughput of the system. Why do we improve the throughput? Because these operations is done all at once across the many DRAM columns inside a DRAM subarray. So in a DRAM subarray, we have thousands of DRAM columns, around 65,000 DDR4 chips. And you can, when you do this activation, you activate all of those cells at the same time. So all of those columns are basically working together to do this Boolean and or not operation. So you basically now have a really wide SIMD machine inside the DRAM chip capable of executing these copies and DRAM majority operations. In terms of energy, we see also some significant reduction when compared to those Boolean operations inside a CPU as well, because you're not moving any data out. So we use these Ambit substrates to accelerate some applications that actually do those bulk bitwise operations. That's, for example, database query. And we see some significant improvements compared to the CPU and GPU. So, okay, we can do in-DRAM row copy, we can do initialization, we can do majority, or, and not. So it all seems nice, but how often do you write application that does in-DRAM or does OR operations, right? It's quite infrequent for that to happen. So you need to have some sort of arithmetic operation in the DRAM chip itself, so we can make that that operations more useful for more applications. So that was the work that we did in, oops, I lost my thing. In ASPLOS 2021 called SIM-DRAM. So the main idea of SIM-DRAM basically is to leverage those in-DRAM primitives, those in-DRAM row copies and majorities to compose more complex operations and later on allow the application to use those operations. So based on that, we create this three-step framework, which basically takes as input a desired operations in the form of circuitry like and or not, like for example, think a RIP carry adder. Then in the first step, we convert that circuitry into its optimized circuitry using only majority and inverted graphs, basically because the underlying computation that you are doing when you're doing in-DRAM computation is majority, as I mentioned, right? So if you use, if you go for Boolean circuitry down to majority directly, you're going to end up having to do more triple row activations to realize your computation, which is going to be costly. We can reduce this number of in-DRAM activations by using majority algebra itself and some CAD circuitries that minimize majority-based graphs, so that we reduce the number of gates that you're going to use for computation, and hence the number of triple activations that are going to be mapped to in-DRAM operations to realize that operation itself. So then after that, we basically have a circuitry that only has majority and inverted nodes over there. And then we convert that graph into series of in-DRAM row copies or in-DRAM majority operations as needed by basically traversing that that circuit that was generated in step one. We call the sequence of operations that is generated a microprogram, which is basically a recipe that tells the memory controller how we can realize that in-DRAM operation itself. Then we add that microprogram to a special region in DRAM to be further used, and also as a CPU ISA for the programmer to interface with. So after that, the first two steps are offline and done only once. So if you want to implement addition, a subtraction, a multiplication, a division, you do it once and generate those microprograms. And eventually, when the application wants to use those in-DRAM additions or subtractions, it triggers that operation using that newly added CPU ISA in its program. And then we implement a control unit in the memory controller that goes through that microprogram, again, the recipe that tells how you implement that instruction, and issues those in-DRAM row copies or in-DRAM majority operations to the DRAM chip itself. So I'm not going to get in details on how those were implemented. What I'm going to show is an example to try to make it a little bit more concrete. So let's say that we have two vectors, vector A, B, and a carry in. A and B always stores 1 bit. Each bit is 1. And I have as many elements as I have columns in the DRAM chip itself. And what I want to do is I want to add A and B. So I want to add 1 and 1, and I want to get 2 in the end. So the way that SIMDRAM is going to work, first, I need an adder. So I take a root carry adder. It can be any adder. It can be cobblestone, whatever you want. You take this adder. Then you put that adder into the SIMDRAM framework. The first step is going to translate this adder that uses Boolean gates into an adder that only uses majority and not gates. And then what is left for me to do is traverse this graph here, node by node. And instead of using logic gates to implement these majority gates, I'm going to issue triple row activations to trigger that in-DRAM majority operation to realize the computation. So basically, I go gate by gate here in this graph. The first gate takes as input A, B, and carry in. So basically, I issue a triple row activation involving the row A, B, and carry in, and then the output is going to be the majority of 1, 1, and 0, which is 1, and I store this data into this temporary carry out row. Then I go to the next gate and I issue again a triple row activation involving now A bar, B, and the and the carrying again, and then I generate another output for the temporary row, which now the majority is going to be of 0, 0, and 1, which is 0. Finally, I go to the last gate, which involves the input A and also the 2 previous generated temporary data. And then I issue that triple row activation, and now I have a majority of 1, 0, and 0, which is going to be 0. So what I have in the end is the implementation of these sum operations inside 2 different DRAM rows, the carry out and the sum row. And then if you go from carry out to sum, you have 1, 0, which is 2. So basically, we realize that in DRAM addition inside the DRAM chip itself. So we use this SIMDRAM framework to implement 16 different in-DRAM operations. So addition, subtraction, division, multiplication, ReLU operation, and some other ones. And we compare the throughput of those operations with CPU and GPUs, and you see significant improvement. And we use those operations to accelerate 7 real-world applications, including some neural network inference, and we see some significantly improvement again compared to the CPU and the GPU. So, okay, we can do now in-DRAM row copy, we can do in-DRAM Boolean operations, we can do in-DRAM arithmetic operations, right? All of this is really nice. I have now this in-DRAM substrates that became out of the blue was only storage. Now it basically became a very wide SIMD engine, right? Because as I mentioned, we are doing this single operation, like think about the addition across all of those thousands of DRAM columns at the same time. And as I mentioned, those are quite a large number. So basically now I have these substrates that became an in-DRAM SIMD engine that I can use to accelerate my applications. So, okay, is this good enough? Can we leave? The answer is not yet. The problem is that this is quite an old problem for that VLW machines suffer from in the past as well, and also very wide SIMD processor-centric architectures, is that if you have too much data to feed to a processor that depends on that data to use throughput, often you're going to end up in the problem that you don't have enough data to feed to that processor. So the question that we are trying to answer in this follow-up paper that I'm going to mention next is that how often you have an application doing addition over 65,000 elements at the same time. And not only 65,000 elements, it needs to be always multiples of 65,000. So if it's half of that, then your utilization of your substrate is going to be half. And if it's 1/3, it's going to be 1/3, so on and so forth. even though like your data might be really large, you're still going to have a tail that's going to eventually lead to underutilization. So the problem to make the problem more concrete, the problem that we have here is that this now very wide in-DRAM SIMD engine suffers from underutilization because it has a really large and fixed computing granularity of the size of the number of DRAM columns that you have inside the DRAM substrate. So this creates a SIMD underutilization, which leads to both throughput loss and also energy inefficiency. And now I have to, for example, pad data to fit into those 65,000 columns, and that pad data is going to be activated and is going to generate extra, going to consume extra energy, which goes against our initial motto of process memory of reducing energy consumption. Also, I don't know if we already catch that from the examples. I'm always taking 2 arrays and generating a 3rd array. I'm never telling, it's always like this. What if I need to reduce that array into a scalar? If you need to do that, then you need to move back to the CPU because there is no communication across the different DRAM columns in the DRAM subarray, so that you cannot move the data across columns freely, so that we can realize, for example, a reduction operation without the assistance of the CPU. So basically, we are constrained to only do embarrassing parallel map operations using the substrate. The 3rd problem also was, maybe you catch that from the SIMD-RAM part, is that programming this now involves me to almost program like an assembly, because I need to use those new CPU ISA instructions that are added to the CPU ISA, and manually program that and align data inside the boundaries of the DRAM subarray and all of the complexity that involves manually without the assistance of a compiler, for example. So to summarize, the problem that we have here is that this rigid granularity for in-DRAM computation limits its applicability and efficiency, and our goal is basically to fix that. So the key idea for us to fix that is, again, an old idea that was implemented in other systems, which is called fine-grained DRAM access. So when you access a DRAM row inside, when you're doing that DRAM column access that I mentioned in the background, you open or you activate the entire row at once. And this happens because there is a global word line that spans across all of the different columns inside the DRAM subarray itself. Independently if you're going to access only portions of the DRAM row in the cache access or not. Then prior works have realized that this is a problem for efficiency of systems. This is not related to processing memory. And they propose what is called fine-grained DRAM architectures, which basically segments that global word line that propagates across the different DRAM columns, allowing you only to access the portions of the DRAM row which you're going to follow up. You're going to access in a follow-up cache column request for that particular DRAM row, and this improves energy efficiency for some applications. So we are going to use the same idea of fine-grained DRAM now for processing using DRAM computation. So this provides 3 main benefits for processing using DRAM architectures. The first one is that we are going to improve SIMD utilization. So if your vectors are 1/5 of the 65,000 columns that I mentioned before, we just allocate that 1/5 of the DRAM subarray for that computation itself. Sorry, you have a question?
How are you breaking that? Are you actually putting more word lines in? I mean, more word lines in, or is there something gating off?
There is something gating off. I'm going to mention the array itself, but is there some isolated resistors over there? So the first thing is that we can allocate as much computation that we need for that target processing using DRAM operation, hence improving SIMD utilization. The second benefit that it provides, and the name of the paper comes from there, is that if I have a DRAM subarray and I have half of my DRAM subarray doing one instruction, and I have another instruction that is data independent from that one that is currently operating, I can dispatch that instruction in the queue to the same DRAM subarray, and now I don't operate anymore in a single instruction multiple data model. I operate in a multiple instructions. I have multiple in-DRAM instructions executing over multiple data inside a single DRAM subarray at the same time. So if you notice, I'm slowly building a computer out of DRAM cells. And of course, it adds on complexity on control and all of those things, right? Which I'm going to briefly mention next. So the next thing that this allows is that inside the DRAM subarray, there are some interconnects that moves the data out of the DRAM subarray into the DRAM columns, the DRAM I/O itself, to eventually get to the memory controller. So you can use those interconnects to move data around portions of a DRAM row, hence realizing more complex computing patterns like in-DRAM reduction operation. Finally, a nice feature of this fine-grained DRAM access is that usually they operate at the granularity of 512 columns, because there is a other instruction in the DRAM subarray called DRAM mat, which is composed as this size. This is a design decision that is done when you are manufacturing the DRAM subarray to improve signal integrity and reduce costs. So those 512 DRAM columns, now each column operates as a SIMD lane. I can use now AVX 512 instructions and its compiler support to map those AVX 512 instructions into process used in DRAM operation. So if I have a AVX 512 instruction that does addition, and this addition is now looped and is creating memory bottleneck, now I can just take that instruction, translate to in DRAM addition operation, and map that instruction independently from the programmer to the substrate itself. So basically, we leverage this idea of fine-grained DRAM in both hardware and software level. I'm going to really briefly mention all of those. So in the hardware side, first, the modifications to the DRAM chip itself, we segment that global word line using some isolation transistors and add some selecting logic, which allow us to select which regions that you want to activate for that target processing using DRAM operation. We also append that global interconnect network that I mentioned before with extra muxes to allow us to move data across different DRAM columns for in DRAM reduction operation. You also complicate a little bit the control unit in the SIMDRAM paper so that we can schedule, dispatch, and execute multiple data-independent process using DRAM operation at the same time. On the compiler side, we leverage that idea of leveraging vector instructions by implementing 3 LLVM compiler passes responsible for identifying loops in applications that can be automatically auto-vectorized into regular vector instructions. Then we schedule those vector instructions as process using DRAM instructions, and we append those instructions with some metadata to tell the hardware that instruction A and instruction B are data dependent. They need to be executed around the same region in the DRAM subarray. Instruction C is data independent from either of them, and I can execute them concurrently from with A and B. And finally, I have some code generation routine that generates the final binary. So we evaluate all of this in simulation and based with 12 real-world applications, and we see that by implementing computation like this, we can do in DRAM operation. We can accelerate those applications in terms of performance efficiency. And that was a MIM DRAM. So, okay, we can do in DRAM row copy. We can do in DRAM majority. We can do in DRAM arithmetic at a large granularity, at a finer granularity. What else is there missing for us to make this a full-blown useful execution engine, right? Basically, what you are missing is transcendental functions like sine, cosine, those functions that are hard to approximate. You can approximate using, for example, coordinate functions, but that will require a lot of arithmetic operations. To solve this issue, we implement something called Pluto. And the key idea of Pluto is quite an old idea. We are going to use lookup table implemented in DRAM to trigger transcendental functions like those sine and cosines. And then we are going to implement what we call a Pluto loop query operation, which allows us to have a high throughput lookup table query implementation inside the DRAM chip itself. So in the interest of time, I'm not going to go into details on Pluto, but what I'm going to talk next is that all what I just mentioned here, everything that I just mentioned here, all of that was done in simulation. So we understood the way that a DRAM chip works, and there is basic principles. And then based on that, we thought that those operations are feasible to be implemented. And we conduct simulation, both Sparse simulations or architecture simulations, to develop those in-DRAM operations itself. However, there was always this question: can you actually do it in the DRAM chip, in the commodity of the shelf DRAM chips themselves? Because basically, as I mentioned, you are not adding much logic to enable things, especially for in-DRAM row copy and Boolean operations. You are just operating the DRAM chip in a different way. So basically, we have this paper that was presented in HPCA this year, which Ataberk is going to talk next, that shows that by violating DRAM timing parameters, we can actually perform a subset of those in-DRAM operations in commodity off-the-shelf DRAM chips as they stand today. So this is a quite interesting result because it shows that DRAM chips are very capable of doing a subset of this anyway. It's just sitting there waiting for us to leverage that for us to accelerate our memory bottleneck applications. So I'm not going to get into details. Ataberk is going to talk more about how that is done next. What I'm going to mention is that those in-DRAM in-memory operations that does not use this extra logic for computation is not limited to the DRAM chip itself. So SRAM arrays are capable of doing something similar using different approaches, and also flash storage flash chips are also capable of doing in-DRAM, in-flash book bitwise operations by doing AND or and then operations as well. And we have this work called Flash Cosmos, which shows that by a similar idea, by activating many word lines at the same time, or sensing in this case, because it's flash, many word lines at the same time, you can generate those book bitwise operations using flash cells themselves. And similar things can be done using emerging memory technologies, where you can implement in situ multiplication dot product operations by following a Kirchhoff law, basically. And these operations are being used to accelerate, of course, neural network inference, because it maps really nicely. So I'm not going to go into details on those because we are over time. But hopefully you got more or less the key idea of those things. I don't know if there's any burning question that I can answer. If not, let's go for the last talk, and then you're done. Thank you so much again. You have the mic?
Yes, you downloaded them already. Does the mic work? You did open them, so you won't see them there. Is the microphone working fine? Hello, hello.
So here's working.
Yeah, then it's working. Okay. Where are the slides? I have my pointer here. All right. Cool. Okay. Thank you for those who have stayed until the last talk. If you want to or need to leave, please feel free to leave. I don't mind. During the talk, you can just exit the room. This will be about infrastructure for processing using memory research. This is to close the loop and show you how we can perform some of these operations that we talked about in real DRAM chips and the infrastructure that we use and develop to do that. That's me. I'll skip this slide and go back to it if you find any of this interesting and you want to learn more. These are the 4 papers I will mainly discuss in 30 minutes. I have too many slides, but I won't cover all of them, especially these ones. We will be looking at processing using DRAM specifically in the vast space of processing using memory or processing in memory. We already know we can perform a bunch of operations like bulk bitwise and or not majority, copy initialization with 0. There's also some other more the security applications that can benefit from true random number generation and physical unclonable functions, and some lookup table based complex computation that Geraldo just mentioned. We can do these we proposed some solutions or designs to do this at low cost, but we can also use analog computation capability of DRAM without any change to the core DRAM array and implement these operations, or a subset of these operations really, using what we call multiple row activation, and I'll go into a bit more detail on that. With this, we can perform these operations even in commodity off-the-shelf DRAM chips. And this talk will be about that. So we'll start with PyDRAM. It's an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. I'll skip the DRAM organization background that you already know about from the last talk. And maybe I'll mention how we access a DRAM array. This is a different view of a DRAM subarray, where we basically concatenate multiple DRAM cells in a row to form cache lines. Each cache line will have approximately, typically 512 bits. I'm showing you this because this defines the access granularity to DRAM chips typically. So you would be activating a row to retrieve the row to the sense amplifiers. And once the data is in sense amplifiers, you can send read commands to read data in cache block granularity, or you can write to the sense amplifiers again in cache block granularity. Now this is depicting you trying to access another DRAM row. And to do these, to access a DRAM row, we send an activate command. To access another DRAM row while a row is open, we send a precharge command. These are the 2 key commands that we will be using to perform in DRAM operations. And there are some latencies that we must obey that are defined in the DRAM interface standards that tell us how much we should wait between subsequent DRAM commands. 2 key examples here are activation and precharge latency. Those are between subsequent activate precharge commands and a precharge and an activate command. We have seen some processing in memory techniques. Some commodity chips, DRAM chips, when we were working on PyDRAM, we knew already could perform a subset of these operations, such as row copy. You could copy data and row granularity in DRAM chips. You can perform, you can generate true random numbers, and I'll go into a bit more detail on that later. You can implement physical uncallable functions. Again, we will touch on that a bit later, and majority operations. Now, I'll be talking about these 2. Those are row copy and true random number generation. And we will be using the key ideas of what Geraldo already described, row clone. So I'll skip this. And I'll show you how we perform row clone in real DRAM chips. It's nothing new, really. You send this activate precharge activate command. The catch is you violate those timing parameters I talked about that we must normally obey if we want to make sure that our DRAM chip operates correctly. So it's a pictorial depiction of what happens here. Let's say that you're activating row S and then activating row D. If you obey the timing parameters and use whatever value specified in the DRAM standard, you'll get this operation. And like in this order, you activate row S, then you precharge the bank. So no row is open at that point. And then when you activate row D is open. That's it. That's how DRAM normally operates. But if you violate the timing parameter, that is kind of reduce the gap between the first activate command, the precharge command, then basically the precharge command is ignored by the DRAM chip. So this is something the designers probably thought like, okay, this is defined by the standard. Any memory controller will obey these values anyways. So we can maybe optimize for cases where these timing parameters are not obeyed, but maybe they have a design that kind of is can be implemented at lower cost if you assume that no one will not obey these timing parameters. Again, I won't go into the details of why we think this happens when we violate timing parameters, but I can refer you to some of our works which have hypothetical row decoder circuitry that explains this behavior. That's the key. This timing violations will be the key to performing processing using memory inside commodity DRAM chips. I'll maybe touch on the key idea of the in DRAM to random number generation, because this is different than what we have seen so far. The basic idea is this is showing you another view of a subarray with differently sized and colored DRAM cells. The darker red colors indicate cells that fail with a very high probability when we access them, with again a reduced access latency. This time the latency between an activate command and the following read command. And then there are cells that have a very low chance to fail when you again access them with reduced access latency. And there are some cells that fail with close to 50% chance. That means if you were to access the cell, the function you get out of that cell is a random number generator, basically. If you can find these cells, identify them, and just continuously read them, you can generate random numbers at high throughput. And because we can already violate timing parameters, commodity DRAM chips already can generate random numbers. So we have seen these cool applications so far. I mean, in the 6 hours in this workshop or tutorial. But how do we enable them, right? This is an important, I guess, problem that Brian's talk also addressed to some extent. Basically, we have bulk data initialization, let's say an application at the highest level in the system stack. And then we want to back this operation up with in-DRAM row copy operations at row granularity. So there's like a gap to bridge. So you would implement some support for custom timing parameters. Those will be the violated timing parameters at the logic and microarchitecture level. Some control logic for PIM operations, you know, like your maybe processor will tell the memory controller to, okay, do this operation and then give me back the data you get. Some software interface to execute these processing and memory operations to the application or to the OS. And then again, supervisor or OS that basically gives the basic support, provides the most basic support that will be mostly about data mapping and virtual memory for these applications. And PyDRAM essentially tries to bridge this gap with customizable hardware and software components. And in doing so, our goal is to allow users to rapidly implement PIM techniques, solve their system integration challenges, and analyze end-to-end implementations of processing in-memory techniques. It has 4 key components. I won't go into the details of these. Essentially, in the hardware side, we have a processing and memory operations controller that instructs the memory controller to perform operations, and then a custom memory controller that supports issuing DRAM commands with modified timing parameters. On the software side, we have what we call a PIM operations library that is interfaced with the custom supervisor software. And the supervisor software support has basic system support, such as data, that basically helps you map data. Like the user program can use whatever functionality, new functionality we implement to map the data in a way that you can perform in DRAM operations on it. And I won't go into the details of that. We attach these components, these 4 components, to a real computing system. It's a low-cost RISC-V Rocket CPU core and a real DRAM module in this FPGA prototype. This is a Xilinx board that has this RISC-V system in the FPGA, implemented in the FPGA. And this Micron DRAM module, for the interested people, that we use as the PIM-enabled DIMM that we perform these operations on. We also, in this work, we identified two challenges in implementing row clone end-to-end. Those are memory allocation and coherency problems. For coherency, we implemented CL flash in the RISC-V CPU. So basically, just to describe the coherency problem shortly, you will have data in DRAM. You're operating on data in DRAM, but your processor might also have cached copies of the data that you're operating on. So you need to make sure that nothing gets like you don't have stale data in your processor cache as well. You operate on old data in DRAM, right? And the solution, we went with the simplest solution in this case, which is to flash all the data, make sure you don't have any cached copies of the operands that you're working on inside the DRAM chip. And to do that, we had to implement CL flash instructions in the RISC-V CPU. And for memory allocation, I'll go into a bit more detail, the problem of memory allocation. Here, I'm showing you 3 example allocations that don't work. If you have your source operand not completely occupying a row, and you want to move this or overwrite target 1 with that data, what ends up happening is this part of the row that's not occupied by source 1 will overwrite this part of the row that's not occupied by target 1. So you want really full rows. Your operands must be the size, must be multiples of row size. The second one is where you have an alignment issue. The indices of source and target operands with respect to the beginning indices of the rows are different. So you don't want this also. And you want the rows to be really in the same subarrays, because in DRAM, row copy operations cannot move data between subarrays, across subarrays. And the fourth one satisfies all 3 requirements here. So I'm going to leave this, I guess, as food for thought. I mean, in the paper, we implement a memory allocation technique that can provide you with the 4th allocation, but I'll have to refer you to the paper for those details. And we evaluated how row clone would perform in such a system, then in this system that we designed. So I'll just flash some results. These are showing you the throughput improvements you could get if you have support for in-DRAM row copy operations, for initialization and copy operations for different array sizes. Here, basically, if you have an 8 megabyte array size, you're seeing the benefits of using in-DRAM copy compared to the Rocket core, the in-order core copying this data from an 8 megabyte array to another 8 megabyte array. And for initialization, you're seeing that same thing, basically, versus the Rocket core. And versus that Rocket core, you can have a lot of performance improvement. But part of the reason why this improvement is so high is because the Rocket core itself is too slow. It's a 50 megahertz core, which we had to go with in case of this first version of the infrastructure, let's say. And then we have an ongoing work that tries to bridge the performance gap such that the CPU in this system represents a real-world CPU. Okay. I'll move on to the next part of the talk. Basically, that's it for PyDRAM. And if you have any questions, I'll love to answer it right now or later. Yeah, I mean, I'll skip the derange part also. We implement support for in-DRAM through random number generation as well, and we evaluate it as well. And it gives us not so bad through random number generation throughput, considering this is a real system from a DRAM chip. This is the summary of our work for your reference. Everything about PyDRAM is open source, and this you can find it at this link. And we're happy to basically help you develop even further these infrastructures, or help you install one in your workplace or research lab. An extended version of our this was published in ACM Taco, so it's a journal paper. It's available on archive. And then I have a longer talk on YouTube where I describe how you can use the infrastructure in much more detail. We don't have just PyDRAM, so we have an older infrastructure, SoftMC, that we use to characterize real DRAM chips. A bunch of aspects of it, retention times, or maybe redisturbance failures, like RowHammer that Geraldo talked about in the first talk. And this is the first version of this sort of infrastructure that allows us to test DRAM chips at a very low level, like at the level that the DRAM interface provides you with. And this is an even newer version that allows us to test these different sort of DRAM chips from basically DDR4 DRAM chips using 5 different FPGA boards that's already like available out of the box. Again, this is all open source. You will find links to it in upcoming slides. I'll talk about this more 7-8 minutes later, but I'll go back to this functionally complete Boolean logic in DRAM chips paper that Geraldo flashed before leaving the stage to me. Basically, we use that infrastructure to show that DRAM chips are already quite capable in the sense that you can implement functionally complete operations, a Boolean logic in DRAM chips, and you can open many rows, a lot of rows. So this first work that I'll describe shows for the first time that you can simultaneously activate up to 48 rows in total in 2 different subarrays. So that's the new component that it adds to the state of the art. We didn't know we could activate we could activate rows from 2 subarrays using only 2 activate commands. Using that, you can perform NOT operation with up to 32 output operands and 16 input and NAND or NOR operations. So the key idea, again, is to use this activate, precharge, activate command sequence with reduced timing parameters. When you do that, when you're targeting a row from one subarray and another row from another subarray, you see that up to 32 rows can be activated in one subarray and up to 16 rows can be activated in another subarray. This is empirical observation, basically. We don't have the full picture or like all the insight that we can have into the DRAM chip to explain you in more detail why this exactly happens. But we have some hypothetical circuits. Circuit designs, yes. So let me walk you through the key idea of the NOT operation, and then we'll go over an example that shows how you can do NAND, and NAND operations. But basically, if you look at this depiction of a sense amplifier, this simplified depiction of a sense amplifier, and 2 cells on either sides of the sense amplifier, you see that the sense amplifier really operates as a NOT gate. So if you have the source data in one cell in one end of the sense amplifier, that's one subarray, and you want to put the negated value to another, so to this destination cell, what you have to do is you activate source. So that will get the data into the sense amplifier. And then once that happens, the other end of the sense amplifier is already driving the other bit line that goes to destination cell with the negated value of A. At this point, you simply have to make sure that you enable the cell. And then the value that you have in the bit line will overwrite the value in the cell. That's really the key idea of the NOT operation. For NAND, NOR and an OR, it's a bit more hard to convey, but I'll try my best. Basically, you have, again, the same depiction, but we have multiple cells on either side. And now we have the the concept of reference voltage introduced here. So you will basically do multiple row activations. You will activate all of these cells at once. And then we will have basically as the voltage levels on either on the 2 bit lines, a function of the voltage level of the cells. And this function will basically, there are 2 functions, and the sense amplifier compares these 2, the results of these 2 functions. And using that, using that, you will be able to implement a wide variety of functions. But I'll only show you and then NAND so that this becomes a bit more concrete. I cannot give you all the details I need to give to make this explanation stick, unfortunately. But hopefully this example will be useful. So you have, again, the same picture, just a different style. You have the reference, what we call the reference subarray on top of the sense amplifiers, and what we call the compute subarray on the bottom of the sense amplifiers. The distinction between them is basically compute subarray receives the operands that you want to operate on. And the reference subarray is just full of values that you configure before you do the multiple row activation to ensure that you get the correct output. So we will fill one row with, basically, we will store a voltage level of VDD in one cell, and half VDD in the other cell. This is something we can do using what prior work frac DRAM showed. And then in the compute subarray, we will store the operands. That's X and Y. We will do our act pre-act sequence. And then this will lead to the voltage level depicted by this function here in the reference subarray. That's the average of VDD and half VDD, and average of X and Y in the compute subarray. So let's see how this works. We will build a truth table for AND and NAND operations on the right. We have the X and Y equals 0. That means we have a ground voltage in the compute subarray, and the reference subarray's voltage does not change. It's always 3 VDD over 4. The sense amplifier will compare the voltage on these bit lines, and then it will amplify the voltage level to the direction of the reference subarray, because that part, well, the reference subarray had higher voltage than the compute subarray. And the compute subarray receives a voltage level of ground. So that's essentially, well, encoded as 0. And this is the first combination of operands we have. And then the next combination of operands, we still have the same result. Basically, the only difference is the compute subarray gets a VDD over 2 as the average of these two values. And then when you do the comparison, you do the same thing again. So the compute subarray gets ground and the reference subarray gets 1. For operands 1 and 0, you still have the same average voltage in the compute subarray. So the same thing ends up happening. Now, when you have both operands as 1, this is where the interesting different result happens. Basically, you have VDD in the compute subarray. This time, when you do the comparison, the voltage level deviates to the direction of the compute subarray. So you have 1 in the compute subarray and 0 in the reference subarray. And if you look at this, basically, this is an AND of the two operands, the compute subarray voltage level. And the other one is a not AND of, well, the X and Y operands, basically. That's how you go by implementing your function with functionally complete DRAM. And you can see more about it in the paper. And the rest is about detailed characterization of how, well, how the success rate, that's the number of correctly performed advised operations, change from operation to operation, and then with data patterns, and also with temperature and other factors. In the paper, you can find more details. Maybe one remark I'll make, like this key limitation, one key limitation of processing using memory using real DRAM chips is that you won't be able to have correct operation in every single bit line all the time. So you'll have to deal with errors to some extent with some techniques. One commonly used technique is to simplify the bit lines that are not reliable, as in you don't really perform these operations correctly in those bit lines. You will not use them. You'll try not to use them. It's a sort of like blacklisting approach. But yeah, otherwise, I would say this is an ongoing sort of, an open research direction. Okay, I think that's all I would wanted to say about processing using memory or processing using DRAM and infrastructure for processing using DRAM. I think the rest we don't have to cover. You mean, yeah, maybe I'll add a shameless plug, not only because it's something I'm presenting in like this Tuesday. That's SMD. Let me just talk about this really quickly. So this is self-managing DRAM. We'll talk about this in session 7A to this micro. That's Tuesday, 2 p.m. room A. Why I'm talking about it, or the relevance of PIM, will be clear after this 5-6 slides. I'll go over it really quickly. Basically, I'll make some claims, and I hope you trust me on this. So the DRAM interface today is completely controlled by one side. That's the memory controller, because the DRAM interface is defined in a very rigid way. And there are maintenance mechanisms that we must perform to maintain DRAM data integrity. And these maintenance mechanisms, we're going to need more efficient maintenance mechanisms as DRAM scales to smaller technology sizes. And these mechanisms are defined in the DRAM standard, which is in turn defined by a committee or a committee of more than 300 companies. That's JDAC, who also develop devices that obey the standard. Because of the amount of work involved in doing that, the DRAM standard itself poses a barrier to implementing new maintenance mechanisms, basically, because you would need to, when you want to implement something in the DRAM chip, you would have to make sure that the DRAM interface is also modified to reflect those changes you did. And this happens because the DRAM interface is defined in a rigid way today. And our key idea in SMD is to allow the DRAM chip to control maintenance operations, so yielding some of the control from the memory controller to the DRAM chip, and allow the DRAM chip some control over its own interface. And that allows you to implement new maintenance mechanisms without modifying the standard and exposing DRAM internal proprietary information, which is maybe interesting for DRAM manufacturers. But why I'm talking about this is, in the paper, we implement a bunch of use cases to demonstrate the usefulness of this idea. And one thing we discuss is processing in and near memory. And this is some excerpt from the paper, but the basic idea is you have seen some processing near memory architectures like UPMEM, which have compute units near DRAM arrays inside the DRAM bank. And one reason why you cannot use an UPMEM chip or any such chip as both main memory and compute accelerator, right, is because you don't really know what's going to happen if both the processor and the compute unit wants to access the same data at the same time. So to resolve those conflicts, you can use what SMD uses for maintenance operations. And this text is describing just that, basically, which is to lock a region. That region can be a bank or a subarray where the computation is performed on. And you will not allow the memory controller to access that region. SMD's solution for that is to reject activations coming from the memory controller, and until the computation is complete and the memory controller can now access that region. So that was my shameless plug. Thank you for bearing with it. And if you're interested in that, please visit session 7A. Yes. Yes. Yeah, I mean, again, this is something we did not think deeply or implement discuss deeply in the paper, at least this implementation. It's a really good question. I think that we should be investigating. And I guess we believe that future work, maybe building on SMD, can actually evaluate those sort of different policies and show which one is beneficial or which other one, in what conditions. And this is something I don't have really data to back up. But my thinking is basically there will be some trade-off, but it's good. It would be interesting to see the trade-off. Yeah. That's a good question. I wasn't really. One thing I guess that makes DRAM a good target is that it's everywhere, compared to, I guess, again, I'm not a PIM person specifically, but for primarily, let's say, compared to other technologies that are emerging that are suitable for some types of operations, right? Like memristors, I guess. DRAM is much more mature. Obviously, if you want to implement some fancy computation in DRAM, you would have to still go through some implementation challenges. But I guess the main benefit is really that it is out there everywhere. And then you can also do some of the computation in real chips. Also, that kind of speaks to how impactful it can be, I guess. But there are challenges in either directions. Either directions being, if you want to do computation using real DRAM chips, you have to address the reliability problem somehow. If you want to develop a DRAM chip for the purpose of computation, you have to make sure it's low cost, other things, performance efficient, like it's worth the change and stuff. Yeah. Do you have something to add?
Mostly the DRAM, because I guess over time our expertise as a group went through that direction for, I guess, decisions that Onur made over his career. But we also, as Nika presented, for example, right, we have a lot of people nowadays work on Flash as well. And we have people working on emerging non-volatile memory as well. And we don't do much on SRAM for some reason. We do have some work on processing near SRAM arrays, but we don't tend to go there. Again, it's not for any particular reason other than sometimes we just focus a lot on main memory because, again, is where our expertise is. So yeah, I guess is.
I don't know how to test exceptions. It's a bit more difficult to do this sort of testing and find this interesting operation. All right, I think that's it for infrastructure for processing the memory research. I had more slides, but I'm not going to be able to cover them. Thank you very much for sticking till the end of the talk. If you have any questions, you can find me after the talk here. I won't be moving for 10 more minutes, probably. Thanks.
And I guess that's all. Thanks everyone again.
It was muted. Oh, I don't know since when.
Why are you muted?
Before I gave it to you, I pressed button.
No,
I was taking no. Yeah, got muted just now. So don't.
okay.
Did you stop the live stream?
Yes, true. My computer gave up. Oh, I cannot stop because Gira is the host. Is Gira's computer unlocked?
Yes.
Can you stop there? I'm going to stop on YouTube.